8 submissions, and we select 19 high-quality papers, and each paper is a 5-minute spotlight presentation. And you can see in our schedule that we have 3 sessions, the camera PPG monitoring session, and the other 2 sessions are the camera-based blood pressure monitoring and activity monitoring. And today we will have 2 keynotes from the Professor Achyuta and Professor Ashok. Yeah, and the first keynote is given by Professor Achyuta. So I will give Professor Achyuta a short introduction. So today's the title of the speech of Professor Achyuta is Pushing Out a Pareto Frontier of the Performance Equity via the Computational Imaging. Achyuta Kandabi received a PhD degree from MIT in 2018. He joined the UCLA in 2018, where he is assistant professor jointly of the electrical engineering and of computer science. He has received early career recognitions from the NSF, DRAPA, ARO, Forbes 30 under 30, and has co-founded startups in computational imaging and computer vision. Achyuta recently co-authored a textbook, Computational Imaging, available through MIT Press. So let's welcome Professor Achyuta. Could you share your screen with us and also your video? Yep, Achyuta, could you hear us? Oh.
I made you a co-host, Achyuta, so hopefully that will now allow you to change the settings.
Yeah, great.
Hi.
Cool.
Hello.
Hi. All right. So let me go ahead and share my screen.
Yep. Yeah, the floor is yours. You can start your talk. Thank you.
Great. All right. So give me a quick thumbs up if you can see this slide. Awesome. Thanks. First of all, thanks so much to the organizers for having me here. It's a pleasure to be here. The talk is about pushing out the Pareto frontier of performance equity via computational imaging. And before I start, let me just give credit to the team that worked on this. So the work that I present in general is really now done by amazing students at UCLA and with support from funding agencies. But in particular, I'd like to highlight a few of the authors who are here in New Orleans of the papers that will be discussed. The first authors of these papers are Sasha Vilosov, Pradyumna Chari, and Adnan Armudi. So the first part of the talk will discuss work that's coming up at SIGGRAPH this year. And also Jen Wang and Yunhao Ba are presenting a poster here at CVPR on some work that will also be discussed in the talk. And finally, I'd also like to credit the collaboration with Dr. Laleh Jalalian, who's a physician at UCLA Hospital, who helps us with the clinical aspects of the study, including also IRBs and data collection. Okay, for more about the papers that are behind the talk, feel free to visit our group website, which is in the top link here. So many of us are familiar with the excitement around video to detect vital signs. One of the papers from the graphics community that came out in 2012 was by Rubenstein et al. And discussed Eulerian motion video magnification for revealing subtle changes in the world. Now, I highlighted this paper in particular because one of the key results that they showed was on this subject, where they could actually go and visually enhance the subsurface blood flow to obtain essentially this video shown on the right. So they're magnifying the subtle motions. And in particular, you'll notice that the subject has a kind of a complexion and a skin color that lends itself very nicely to looking at subsurface blood changes. For those of us in the audience with darker skin, we may not see a similar effect, right? We may not blush so often in social settings, which also means that this enhancement would be a little bit different if it happened on us. And so in particular, in about 2020, there was a paper from Nawara, McDuff, and Viraghavan, actually, who are all involved in this workshop and to some degree. I was on the committee. Of course, Dan is a co-organizer and Ashok is one of the other keynotes. And this is a very nice paper that first really drew attention to the cross data set phenomena of how you might have skin type and also gender effects due to the IPPG quality in the waveform. So you can see on the left, you can see some of the amplitude waveforms, and you can see the frequency domain is much cleaner for the lighter skin tones. So after seeing this paper, we reproduced this at UCLA under an IRB, and our results were consistent. We have lighter skin on the left, and we have a plethysmograph method, that plethysmograph meaning it's measuring the blood volume using video. And we're able to see much more robust qualitative waveforms here for the lighter skin. So the next step was to quantify it as well. And in our quantification, this is excerpted from a technical report from Sasha, Pradyumna, and Adnan. We observe a 150% increase in error for darker skin. Basically, you're at about 1.7 beat per minute using a deep learning model to get the high quality plethysmograph, whereas for darker skin, you're at about 3 beats per minute. So that's, even though it's only off by 1 beat per minute, you can look at it that way, or you can also look at it like the error is a 150% increase. You also end up with, if you want to look at this another way of the importance of the problem, you have a 4 times higher device failure rate for darker skin. So what does that mean? Well, let's assume that you were trying to measure the heart rate with such a device just for the sake of exposition. A heart rate monitor is accurate if it's within 10% of the ground truth error. This is according to the AAMI, which is the Association for Advancement of Medical Instrumentation. So 98% of light skin tones in our studies, this is a technical report from the UCLA IRB, met this clinical criteria. Only 91% met it for darker skin tones. And so that's a very significant proportion, because what that means is out of 100 subjects, for example, there would be 2 subjects for whom the device would not work on, whereas there would be 9 subjects for whom the device would not work on if you had darker skin. So that's a pretty significant increase in the failure rate. So of course, there's a lot of work happening in fairness in AI, a lot of pioneering work at this conference, especially with facial recognition started in the earlier days. And one of the things that I'd like to draw attention to in this talk is that fairness can also manifest at the physical layer. So we have light-based devices on darker skin being an example that we're going to cover in this talk, but we also have other types of physical fairness variations. So for example, we have in the photography community, computational imaging community, blink detectors on East Asian faces. We also have some work that's on hip implants that have been described, looking at the gender variation and how hip implants and prosthetics are designed. So there's a lot of physical dimensions to fairness, and it goes beyond algorithms and data sets. And so we had a paper in Science last year that looked at kind of various trace points for where the biases could occur. So you could have biases happening at the physical layer. You could later then propagate that through a computational layer. As an exemplary case, balanced versus imbalanced data sets. And then finally, you have the human interpretation of the data, maybe the clinician that interprets the number that comes out and interprets it differently depending on a subject type. So today's talk is only going to focus on physical bias, and it's going to be in a very narrow setting of skin tone, but I'd just like to point out that there are these other dimensions of fairness as well. Now, one of the questions that often comes up is a Pareto trade-off between performance and equity. Let me just quickly start by saying a Pareto trade-off is a theory from economics, Pareto principle, where optimizing one variable necessarily decreases the utility of another variable. So for example, supply and demand is a classic example. Now, one of the questions that often comes up is fairness and equity a Pareto trade-off? So, for example, some people who believe that there's a Pareto trade-off here will say, well, if we try to make devices more fair, more equitable, we're going to end up reducing their performance on the majority of people, majority meaning the population performance. So the vertical axis here is population performance, and the horizontal axis is perhaps fairness for a protected group. And so to take this to reductio ad absurdum, some people will say, scholars even will say that if you make a device and try to maximize its equity, it minimizes performance. For example, return a random number for everyone. Now it's a perfectly equitable device. It's just not, useful for anyone. So it's a subtle and nuanced question if such a trade-off occurs. I definitely see that sometimes in an engineering system, these trade-offs do occur, and people sometimes get very offended if we mention that there is a performance equity trade-off, and rightfully so. So what we're really trying to do as engineers is we're not actually trying to explore different points on the trade-off ideally. That's not what our goal would be. Our goal would really be to push out the Pareto frontier so we can get both improvements in performance and equity. Okay, that would be the ideal goal. All right, so that sounds like sunshine and rainbows. So how would that actually be tactically achieved? So what are the tactical steps to actually go and push out a Pareto curve? So in the case of the plethysmograph problem, a problem that interests, I think, many of the attendees on this call, you're using images to do that. That's why it's called IPPG in papers. And in IPPG, if you want to consider that there might be a Pareto trade-off, which some of our experiments when we were tweaking image processing algorithms indicated, then an analogy to pushing out the Pareto frontier would be to use maybe a different modality. So for example, combine the photometry with a imaging-based camera with maybe like a radar dish as well, okay? So like a multimodal fusion. So I've been talking about plethysmography often. If you're not familiar with plethysmography, this is an older resource from a webpage that collects a lot of references. And on this webpage, it really describes that the remote plethysmography topic is really one where you have a camera. In this particular case, you have a subject that is in front of the imager. Image frames are extracted, segmented. If you look at the different pixel channels, you'll see a temporal waveform, and based on that waveform, you can do analysis and recover physiological signals. So plethysmography is one such example of a signal. If you do this with a camera, it's called IPPG, imaging-based plethysmography. You can do this with other devices like radar, as I'll talk about as well in this talk. So sticking on the theme of the imaging-based plethysmography, the IPPG fairness or remote plethysmograph fairness, the reason when you use light that it's unfair is that first you have the transmission through the skin being described by the Beer-Lambert law, which is shown at the top here. So here you have this mu, which is a epidermal absorption coefficient. Now, light is not so simple. There's also a scattering component. So you have the Kubelka-Monk diffusion scattering here, which relates the scattered component to dermal absorption and the scattering, a combination of both. So you have two different models for how the light is reflected. And if you actually combine them and expand them and look at the imaging process where you're integrating over a spectral bandwidth, the bottom line is that you can actually theoretically write out the impact of melanin on the absorption coefficients, and therefore the impact of melanin to the SNR profiles. So your SNR profiles, if we borrow from Sam Hassanoff's paper in CVPR 2010 on noise optimal capture, the SNR profile can actually be written in closed form as essentially a functional a function that depends on the melanin content. Okay, so you have this SNR bias in our PPG, IPPG really, it should be imaging PPG. So you have this SNR bias, and this SNR bias can occur at different types of color temperatures of ambient light, different types of color channels, and also different skin melanin fractions will show different degrees of SNR. So if you put that together, if your ideal signal is on the left, the signal that you actually obtain might be shown on the right, which is attenuated. So the goal here is to show that fusion can benefit fairness. And in particular, fusion now will refer to the fusion of an imaging-based PPG with a radar-based PPG. So just to make some quick definitions, you have a modality, M, which is going to be M1 or M2, which is going to be RGB or radar. There's going to be a protected attribute. Now, again, let me not minimize the other dimensions of fairness and also other protected attributes like gender. And other types of demographic parameters are not considered in this talk. This talk is purely about skin tone. It's a very focused talk on skin tone. So in this talk, with loss of generality, we're going to consider the attribute as being light and dark skin. Light and dark skin are going to be defined based on a physician's examination of the skin tone to see whether it falls within Fitzpatrick 1 to or Fitzpatrick 1 to 3 or Fitzpatrick 3 to 6, 4 to 6. There's also an SNR operator, and that's what we're trying to maximize, that returns the SNR of a time series signal. And there's a combination operator, which is what we can kind of play with, which returns the combined signal from signal estimates. So for example, to look at modality 1, which in this case, modality 1 is the RGB. Oftentimes RGB is very high performing. It has very good performance against the population as a whole, right? You can get IPPG down to like a beat per minute using deep learning and modern data sets. So in this particular case, the expectation of the SNR of modality 1, which is shown on the left, is going to be higher than the expectation of the SNR on modality 2. Now, you can also start to make definitions about fairness as well. So the top definition would be a case where modality 1 is better performing. This bottom case would be a case where modality 2 is more fair. Modality 2, remember, is radar, and radar is more fair than imaging-based PPG. I'll explain the physics of that shortly. But you can also have an expression that quantifies that. And so defining a fairness metric itself is an exercise. There are multiple ways to look at fairness, and there will be multiple ways we analyze it. But one simple way is just to look at the expectation, basically the SNR quality of light skin minus the SNR quality of dark skin, and just seeing if it's greater or less than some sort of threshold that you set. Okay. All right. So in this paper, the paper can be, I haven't put the citation here because it's to appear in SIGGRAPH 2022. It's not yet fully out. I think a preprint is on our website, but one of the main results is that if you apply a fusion to this technique, you can not only improve fairness, which you would expect, but you can actually provably show that you improve both performance and fairness. And actually, it's a little bit of a non-obvious result. Because you're combining a modality that is, maybe that's better performing, but not fair, and then a modality that's worse performing, but very fair, right? So is it possible to actually get the best of both worlds, which is you're better performing than any individual modality and more fair than any individual modality? And theoretically, the answer is yes, based on the theory. Experimentally, we get very close. And I think with further study, we'll get to that point. Okay, so now I'm going to change the subject and talk a little bit about radar plethysmography. So in radar plethysmography on the left, I'm showing a radar transmitter and receiver, and on the bottom a receiver. The way it works is a little different than imaging-based PPG, which relies on attenuation. Here, what's actually happening is that as your heart pumps, there's actually a slight variation as blood flows under your skin. There's a slight movement in the skin. Your skin actually moves laterally in Z, if I'm looking head on like this zoom camera at me, my chest is moving slightly forward and backward with my heartbeat. This is not my breathing rate, just to be clear. This is a separate signal from my breathing rate. Now, this kind of heartbeat moving back and forth, the skin moving back and forth, this motion is actually very subtle. It's not by any means easy to pick up. We're talking about things on the order of hundreds of microns. Hundreds of microns are, like putting a few strands of human hair. That's how thick the human hair is, about 20 microns thick. So, hundreds of microns is a very, very small signature. But with a sophisticated high-frequency radar device, you can pick that up. You can pick up these measurements. So in particular, there's a technique called frequency modulated continuous wave radar. So FMCW radar will be able to pick this up. So you'll have an FMCW generator, a transmitter, and some DSP on the back end. I won't go into the details about the mechanisms of this. This will be available online, and we'll have detailed reference guides that you can download if you want to implement your own, as well as a hardware parts list, so you can go shopping if you want to build one. But in short, what's really happening more in pictures is you're sending it's almost like if you're familiar with Doppler radar, it's a very similar concept, identical concept, FMCW. What you're doing is you're emitting frequencies that are changing in time, and then you're catching the frequency at the receiver. And for example, if I emit, let's say, a very fast varying chirp. A chirp is called a chirp is a signal that increases in frequency over time. So depending on what frequency I read, it tells me how much time has passed. That's one way to look at it. And so that's how this diagram is kind of drawn. You have a transmitted signal when blue, and then you have the received signal, which shows a frequency shift. So you can measure that frequency shift by having an oscillator, a reference oscillator, in the receiver, and doing heterodyne detection to actually estimate the frequency. So this is how it looks. This is the device. There's receivers and transmitters. I'll show a different picture of this later, but basically you have a human body, and it's okay if clothing is there because the signals will go through clothing as well. And you'll have transmit and receive into the body, and you'll be sending this chirp, and your output data structure is something called a range matrix. Range matrix is it's like a DTFT in some ways. That's kind of the way the analogy I use, in the sense that it has a multiple temporal axes that you look at. There's a slow time axis on the top, which is essentially, let's say every second I'm doing a measurement, just as an example. Then you have a fast time axis, which is the actual range profile, which is giving you your time of flight, essentially. So every row here is, you can think of this as having your time of flight, and then every column is, every different row is actually a different time slot, and then across the columns you have the time of flight profile. Okay, so this is the actual picture of the device. So in the device, you'll see there's a camera here as well. So we are using a Z camera pair, but we're not actually using the stereo. We're just using one of the RGB cameras here for the IPPG measurement. There's an RF sensor here. And so this is a Texas Instruments 77 gigahertz module. Again, the details will be available on the website if they're not already up. And here you have a receiver, transmitter, power input, and then you have some data transfer. To ground truth, we use Philips MX800 monitor, health monitor. This is what they use at UCLA Hospital. So we did our study at UCLA Hospital, so we want to be consistent. So we ended up getting one of these. Okay, so that's the data capture. There are 91 subjects in the IRB study. The inclusion criteria for the study, we did not include people who were pregnant. We did not include children, but the inclusion criteria did emphasize skin tone as a criteria. Okay, so one of the ways that we can assert fairness is to use adversarial learning. And here's kind of the structure in brief. At the top here, I'll just call your attention to, this is a pretty standard way to now do IPPG, state-of-the-art IPPG, which is just take your RGB data, put it into an encoder to find features, put into a decoder to get the RPPG. There's of course much more complexity there, but in abstraction, that's how a deep learning model that we implement would work for unimodal RGB. In analogy, you can do something with radar, or you can have a deep learning model to take the radar data and extract the PPG, the signal. So to do that, you would take the range matrix as your data structure. This is just a more convenient way to parameterize it, so you're not learning from just massive amounts of radio frequency data. Range matrix is a concise representation. We also would want to window that just to let the network really focus. We're not giving it inputs that are nonsensical. So we window it to the depth range, the time of flight range that we expect the subject to be in, which can be done in a number of ways because you have the peak and it shows up as a clear peak. We then use an encoder and end up getting the PPG waveform as well. So on the bottom, you can see that you can put these two pipelines together in a fusion method. So you take your unimodal networks, and so you make an estimate first of each RPPG waveform. And you can also look at the DFT of that. So you convert it to the frequency domain, almost analogous to positional encoding. Looking at it in different frequencies is actually a very nice input for a downstream model. So we're in the frequency domain and we can go into encoders. So each channel goes into an encoder and we do kind of fusion later on in the process. So we concatenate the features and then we decode it. So nothing special there. So it's basically like a mid to late fusion to estimate now the fused DFT. But now one of the keys is that we apply an adversarial framework to this so that we're actually having a discriminator that discriminates on this waveform being, seeing if it can discriminate and trace the DFT of this waveform as being generated from a light or dark skin type. And the goal, of course, is if the discriminator cannot discriminate that and tell if it was from light or dark, then most likely the network has learned something that's more fair. Okay, so I touched on this earlier. Before I present the results, I just want to give some framing that what is fair and what is performance is itself an open question of what is fairness. And I like to always use this analogy of, I think some of us have heard of this, of the blind people and the elephant. In this case, you have some kids who have closed their eyes or are wearing glasses and they're touching an elephant, they're touching different parts of the elephant, and each person says it's something different, right? The person here would say that the elephant might be a rhino. The person here might call the elephant a snake because he's touching the trunk. The person here might consider it to be a donkey because the tail is similar. And the person here might think of it similar to a hippopotamus, right? So there's multiple interpretations of fairness and performance. And these are the interpretations that we used a bunch of them in the paper just because we wanted to show that regardless of the interpretation, using a few, of a different variety, we wanted to show that the fusion was superior to either modality alone. And here are some of the results. So what you have in these results are a few things. On the bottom, you have bland Altman plots, which is one way to visualize heart rate. You look at the ground truth heart rate, and you look at heart rate error. So you can just look at the spread of dots here between light and dark, and that's going to tell you kind of the fairness of these methods. And so you can look at the multimodal fusion reducing the spread for light and also reducing the spread for dark. You have for example, here you have mean absolute error, right? At about 1.78, this is units of beats per minute. You have mean average performance percentage error, which is 2.35%. Remember, we wanted to be below essentially 10%, which is the AMI threshold. So we're doing very well with actually almost any method. So this is IPPG using PhysNet, and this is radio frequency using our deep learning method. And so you can see that the radio frequency maybe is slightly less accurate. It's at like 2.2 beats per minute versus the color camera is at 1.8 beat per minute, right? So if you fuse them, you can do better than both of them because the signals are orthogonal. It's not like averaging them, right? They each have complementary features. So you can actually get down to 1.12 beats per minute, which is pretty exciting if you start to think about this, because as soon as we start cracking reliably that 1 beat per minute barrier on a lot of different subjects, inclusive subjects, I think then you can really say that the non-contact field that that was pioneered over a decade ago is really comparable to wearables in that metric. In parentheses, you have the fairness. In this case, it's the fairness difference between light and dark. So here, what this means is that if you look at the color camera, you can see how biased the color camera is, right? The error is like 2 beats per minute, but the difference in error between light and dark skin is 2.2 beats per minute. So it's kind of interesting that the difference in error is even greater than the error. That's how far we've come in terms of performance, maximizing performance, but how far we have a way to go to maximize fairness. And if you look at the fusion method, it's not perfect. There's still a bias. It's still doesn't remove bias. There's still a bias against darker skin tones. And again, the fundamental physics of light is kind of playing that role on darker skin, where it's harder to get the signals. And so even with the additional modality, we're getting about 0.67. Now, if you look at this, radar also has a slight bias here against darker skin. If you look, radar, it's the most unbiased method, but even radar has about a 0.5 beat per minute bias on darker skin tones. And there are some things we can't fully explain, so we don't have all the answers. I don't know why radar is still biased against darker skin. It could be that we need to run a larger study. We ran a study with 91 subjects, which is fairly large for this type of study, but we don't have a clear explanation of why melanin would be causing that. It could be other phenotypical factors. So people who have darker skin, the people who have darker skin in our study, many of them were African American descent or from there could be additional phenotypical factors beyond just the skin tone that's giving this bias. So this needs to be investigated further, and so that's something we will do. But in the short term, I think what we definitely have is, compared to if we look at the baseline of a color RPPG device, which is the focus of this workshop and this conference, CVPR, to some degree, I think it's pretty clear now that adding a radar chip to that is significantly better, both for performance and equity. On the right, you have a fairness t-test, which is, it's a t-test that's looking at basically the likelihood of somebody failing the AMI threshold. That's kind of one way to look at it. Is there a group-dependent likelihood of one group being more likely to fail the AMI device threshold than another group? Okay, so as I alluded to, there's a problem here, which is collecting data in a pandemic. This work was done in 2020, 2021, parts of early 2022, and it's not easy to collect data in a pandemic. We're really grateful to the nurses and physicians at UCLA Health. On the right, you can see Sasha wearing a double mask, I think, and definitely some PPE on his hands and so on that you can't see. But he's in the hospital right now collecting data with the multimodal stack. And you can see here the radar chip here. You can see the Z camera above that. You'll also see some additional sensors. I'll describe some additional studies we're doing towards the end of the talk. But yeah, collecting data is hard in a pandemic. So that brings us to the next segue to the talk, is what if we can add data at no cost? And so if you look at this, going back to the Pareto trade-off, if you look at real data oftentimes also comes with its own biases. In other words, real data, you might only have subjects who have particular skin tones. With real and synthetic data, we can hopefully, also use that both for performance and equity to add maybe synthetic avatars and also have synthetic avatars with different types of skin tones. So the problem setup is as follows. So you can take as input, just an image plus a PPG signal. And with that, you can then put that through a biorealistic renderer to get the output, which is synthetic RPPG face videos. There's also kind of this face morphable model that's involved in this paper. So essentially, you create a UV map and have a 3D mesh on which to essentially manipulate the albedo in a way that's consistent with the RPPG signal. We can then overlay a synthetic or a desired RPPG signal that we want the subject to have, and we can overlay that onto the UV maps, and then we can place that through a renderer to generate the synthetic RPPG with videos. So now this is kind of what we call kind of a naive approach in terms of how we would approach the problem initially. We tried this and it didn't really quite work. So the naive approach here doesn't really preserve the vital sign signals here. And it doesn't do that because if you look at the UV map and the mesh is not particularly accurate. The rendering process is not particularly accurate. There's no reason for it to, if you just go and multiply the UV map with this PPG signal, like let's just say you do a dot star with that element-wise multiplication, then there's no reason that after the albedo variation and the geometry variation of the face, there's no reason it would preserve a clean PPG signal. So we want to explicitly control the albedo better. And to do that, it's not just, the PPG waveform is not just based on albedo, but it's based on kind of a biodecomposition of albedo. Because there's a blood perfusion map that impacts how the PPG signals should look. And this blood perfusion map is inhomogeneous. So, the blood map can be obtained in a number of ways. For the epidermis, you can look at the Lambert-Beard law, or the dermis, the Kubicka-Monk theory. Basically, there's work out there, pulse chem and similar, that can actually give you a decomposition of essentially epidermis and dermis perfusion components. So this is the data set that we have. This is another data set. This is a real RPPG data set because we need to kind of have some ground truthing. And so this is the rig. It's not as complicated as the additional sensors. So we can do this. You can see this is in our lab space, actually, where we have a laptop, but we have a camera to capture video, and we just have a pulse ox on the finger. And again, although we're trying to create synthetic avatars, one of our goals is also to do this for more equitable health. So we did collect diverse skin tones in this data set as well. And so this is kind of now what we can start to do is these are all now synthetic humans and synthetic subjects. And so for these synthetic subjects, you can now look at overlaying these digital patients on them. So these are digital patients who are now having reliable PPG signals. So we can now use this, you can imagine, as an input to train our unimodal deep learning methods. So these are some of our results. If you look at PhysNet and now you augment PhysNet with the synthetic data, you can show that like a model trained with both real and synthetic data shows better results on all skin tones. So this is another way to just improve both performance and equity. So these are some results just showing that the synthetic data sets achieve bias mitigation here. So I'll defer this extensive details on the results to the paper. So there's also work that is, we are, we encourage others to look at for a more complete picture. There's been a few papers on synthetic avatars in the last couple of years. So there's a 2020 paper on arXiv by McDuff et al., and there's another 2022 paper called SCAMPS. These papers are remarkable with the size. These papers, I think, really illustrate the size of synthetic subjects that you can start to capture. Some of these papers include 2,800 videos, which corresponds to about 600 gigabytes of data. And I can tell you that collecting such data in a hospital setting, especially in a pandemic, would be very difficult. So the volume of which the synthetic data can start collecting results is pretty remarkable. I think there's definitely an open question on how we do the rendering. I think there's going to be improvements to the rendering across these papers. Perhaps one day to get renderings that have the photorealism of maybe like a deepfake in that regard, but also the physiological consistency in the waveform. And so that's definitely kind of one vector that I think these papers are pointing toward. So, in summary, biorealistic face video generation is interesting. It's nice because it takes some of the work that we're doing in deepfakes at CVPR here in New Orleans, and I think it, among other uses, there are other uses of social good of deepfakes, but this is one good use, I think, of ethical use of deepfakes where it makes sense, turning deepfakes into training data for medical devices. Our synthetic data set can improve the performance of SOTA, deep RPPG methods. Other synthetic avatars are also there that I imagine would show similar results. You can also imagine combining different synthetic data sets as well, different real data sets. So just like real data sets are combined and concatenated, synthetic data sets can be combined, and cross data set evaluations can start to be done. So we're starting to see these data sets being open sourced at UCLA. Since we're presenting the paper at CVPR, we're just releasing our paper around now. So you can come to our poster session and discuss it with us. Jen Wang, who's the first author, along with Yunhao Ba, will be presenting this in the 2:30 to 5 p.m. on the Friday session. Okay, I have just a couple minutes. So I want to just talk about like the future of non-contact sensing at UCLA and beyond. This will be a bias to the work that we're currently doing, but maybe hopefully give some ideas and maybe even some thoughts for collaboration if anyone is interested. So if you look at vital sign monitoring, the duration of measurement that you have can be hours to days, right? And here's a device that you can imagine as replacing some of those tether devices. This is the device that Sasha is collecting data with. It includes what we have in the SIGGRAPH paper, which is the Z camera as well as the RF, but there's these other devices here. And the idea now is to push more towards multimodal sensing, which is going beyond RGB and radar and looking at, okay, what are some of the other engineering modalities that can be used to do this? And if we can do that, I think that we can actually start moving towards detecting disease states with these untethered devices. So if you look at the spectrum of physiological monitoring, you have the vital sign monitoring, maybe on the order of 10 minutes to hours, but you can imagine getting a device that's not looking at sensing vitals in the clinic, but doing this more rapidly. Some of that will require better streamlining our sensing and streamlining our on-edge implementations, but imagine if you could do mass screening, like a triage with a remote device. So maybe you think about, they do this, of course, even before the pandemic due to SARS outbreaks and similar. I think the East Asian countries would often at their airports, Japan being an example, would have thermal cameras that would screen travelers, right? And so you can imagine that pushing the limits of what we can do at the CVPM community could give us mass screening for diseases, potentially including COVID. And that's actually one of the projects we have. We have a DARPA project that's starting on trying to do COVID assessment using this type of detection. This is it in the lab setting. You stand in front of it, ideally for a minute. It captures your readings, and then it spits out your likelihood of having COVID. And the sensitivity and specificity would be combined, compared with chemical tests, as an example. So this is Dr. Jalalian, who I mentioned earlier in the talk. This is now how data is collected. Data is collected very differently for this type of a study. So Dr. Jalalian is preparing to enter a patient's room infected with COVID-19. This is the type of PPE that's used. And Sasha is Alexander Vilosov, goes by Sasha, is collecting non-contact data at the medical center. And so right now, actually, what we're doing is we're trying to find a way to get this into the COVID-19 ward. And of course, graduate students, engineering professors are not quite allowed there. And so Dr. Jalalian is really helping us with the data collection. So that really moves us to also personalized health. Imagine being in one of these wards and having a remote sensor that's able to track you and kind of see how things are going in a way that a regular maybe nurse or regular tethered device that would be intrusive cannot. And so you can also think about, on one hand, from mass screenings, you can think about personalized health being a much longer term endeavor, maybe weeks to months. And so one other study that we're doing at UCLA is sleep apnea. And so we're using these non-contact sensors to assess a person's quality of sleep in the sleep lab over a number of weeks. So there's a study at UCLA where participants come and they're actually in a longitudinal study, night after night, they're coming to the sleep lab. They might even take breaks. They might sleep one night on a Monday, and then the next week they'll come back the next Monday, and they'll repeat this for a number of weeks. But the assessment is to see if we can start to track a subject's sleep through these multimodal sensors, and then potentially do something about it. So again, I'd like to maybe end here in the interest of having some QA. I'd like to also again recognize the group and also the sponsors that make this work possible. Doing clinical and IRB studies is it's pretty capital intensive, and we're very grateful to have some good sponsors. So thanks for your attention, and happy to take any QA.
Wenjin, do you want to handle the questions from the chat? Would you like me to? You're on mute. Wenjing, you're muted. Just 1 second. Sorry about that.
Yeah, I was muted. Sorry. Yeah, thank you, Professor Achuta, for your nice presentation. So anyone, audience, if you have any questions, just maybe raise your hand, or maybe we can just unmute everyone, or we can give everyone a chance to just unmute yourself. You can turn on a microphone and just ask questions. Yeah, and I have actually 2 questions about your presentation. Regarding your fusion between the radar and the camera, I think it's a very nice trend. But you mentioned the sleep monitoring. So the one benefit of the radar is that it is, it does not have the problem of the privacy issue. But now you add a camera to the radar. So how do you think about this?
Yeah, so privacy is an important consideration. I think that's where radar makes more, starts to make a lot more sense. So we're going to be doing a lot of work in radar. For this particular study, it's being done in a sleep lab, and in the sleep lab already, their sleep is being image monitored, either visually by a nurse or somebody who's watching over them. and there are cameras that are recording. So people, I think, would be open to having that in a sleep lab. Now, would they be open to having that in their individual houses and monitoring our everyday sleep? I don't know. Actually, I think definitely it's a risk. But for now, I think what we have to do is see how useful, in other words, if we want to do radar or move toward that, for a lot of these things, camera is much more accurate. Camera has much more information. So I think we need to collect the camera data and show that radar could be as good or as predictive or even better, as an example, than camera. And so that's kind of one of the motivations of doing the study with camera. So yes, it's the longer term issue of privacy is a major issue. But in the shorter term, there's some scientific questions that need to be answered first, I think.
Yeah. And you also mentioned that the measurement of other vital signs, since I think that for radar, you're using the BCG or the SCG. So, but for your presentation, you're still measuring the heart rate. So what other vital signs do you think it's possible to be enabled by this fusion?
Yeah, so I mean, with radar, you can definitely measure different types of motion. That would be like breathing would be an example, respiratory rate. We're also interested in forced respiratory rate, which is kind of the degree to which of difficulty of which you're breathing. With radar, because it's measuring a time of flight and a lateral shift, there is work from MIT Media Lab, from Fadel Adib on using, and Dina Katabi as well, on using emotion detection with radar. So there is some leaps of faith, I think, in terms of what we can do with radar, some miracles that we can do with radar. And so we don't have the answers to all the vital signs that can be measured, but previous publications in top tier venues have shown things that are like within the realm of, commonality or whatever, right? To get the respiratory rate, that's very reasonable and simple. Things like emotion detection, detecting if someone is lying, there are actually papers on doing that with radar as well. So yeah, I think it's an open question.
Yeah, thank you. So for any other audience, if you have any questions, just unmute or raise your hand, and you can ask Professor Achuta.
I think, Wenjing, it might be hard for people to unmute if they're not the host. So I think it's easier if people put questions in the chat. There's a couple of questions already in the chat from Gasper and Dang Dang, and then we can take more after those.
Yeah. Okay, so Achuta, can you see the chat? Maybe you can go through the questions.
Sure. So I think Gasper has asked a good question. Since the precision required for radar in multimodal fusion is at micron level, how problematic is motion? I assume breathing is a source of noise, let alone other movement. So yes, other movement is a source of noise. Breathing itself can be corrected for because it's a periodic and there's some repetition to it. So we are able to isolate breathing itself, but other motion is a nuisance factor. So I think in future work, we are looking at ways to maybe use a depth sensor or maybe using some sort of computer vision model to go and fix some of the issues with radar in terms of the alignment and the precision. So for now, the subject has to stay pretty still. With that being said, even though even though we're moving slightly, it's like the lock-in amplifier effect, which is something to look at, which is that if you're picking up a periodic signal that's buried in a lot of noise, it's actually you can actually do that. So even if you have a lot of nuisance factors, if a periodic signal is there and it keeps going, then you'll be able to pick it up. And that's why if you look at the radar range matrix, we're not just giving it, one slice, we're giving repeated rows at different slow time intervals and then also different short time intervals. And so the answer is that you can move a little bit. You can just stand naturally in front of the radar. You don't need to like bolt yourself down with micron precision, which is impossible, right? So you don't need micron precision in the motion, but if you are moving by, centimeters here and there, then it's not going to work as well. Hopefully that was responsive to your question.
Yeah, and thanks. And the Dandan Shao has the other question.
So what are the major yeah.
Noise to the radar PPG?
Yeah, so thanks for the question, Dang Dang. We discussed the motion artifact. Other noise sources are, of course, just signal to noise ratio, signal integrity. That's also kind of a major noise source. I think the physics of motion, the clothing that's happening a little bit to some degree, depending on the type of clothing. You also have multipath interference as well. So there are various noise sources. I would say the main noise source, in my opinion, is motion artifacts. But it's also a little bit up to interpretation. I think unlike cameras, I think there's actually a lot less work in radar health monitoring. I think more recently, the SIGCOM and MobiCom community has moved towards the use of radar for sensing over the past half decade, whereas we've been using cameras for about a few decades to look at health monitoring. So I think that it's kind of just an opinion of what's most significant.
Yeah, there are two more questions. Can we synthesize the radar signal along with the video data?
Yeah, that's a great question. We didn't do that, but that could be the next paper.
Yeah, and the other question is that for the radar, even if the subject is not moving voluntarily, there's always slight tremor present in all the people. How does this affect the radar accuracy?
Yeah, so that's again a question of motion. So it's I haven't, we haven't characterized that tremor, so I don't have a clear answer for you on what that tremor is. But again, like if you're locking into a certain frequency in the range of the heartbeat, then everything else becomes a lot more nuisance, and you can avoid that. So for the motion questions, I would direct all those right now to the lock-in effect, and leave it at that for the moment. I think, as I mentioned earlier, big motions and the tremor that Gil is mentioning may reduce our signal quality, and maybe if we corrected for that, it'd be better. But I don't have a clear answer on because I don't understand the tremor well enough to answer it.
Yeah, and what do you see are the biggest barriers for bringing IPPG or radar PPG technology to clinical applications? I think that's a good question.
It's a good question. I think there's a huge barrier to doing this in my experience. First is, I think a lot of clinicians are uncomfortable with the use of a remote monitoring device compared to a wearable because they want the highest quality signals. And right or wrong, a wearable is always going to be better, I think, than anything we can do remotely. So for the clinical setting, there's a lot of questions of, well, we have access to the subject listens to us because we're physicians and nurses, and they're going to listen, so we can have them wear a patch. There's no need. All I need is the best quality signals and monitoring and stuff like that. So I think that we can talk about patient compliance being one of the areas where maybe patients would be more compliant with something that's wireless. But I think where it really makes sense is outside clinical settings. It's maybe bringing, I've been a lot of meetings at UCLA where it's really about doing clinical things outside the clinic, if you know what I mean. Like, for example, turning a classroom like a lecture hall at UCLA. Some of our classes could be like 400, 500 students before the pandemic. And if you have a screening kiosk for 30 seconds that scans someone, or you can get it down to even 1 second, as soon as they come into the lecture hall, and then we can tell them to stay home if they're sick, that is bringing a clinical problem out into a field where, you know, wearables would not be possible or scalable. So I think areas where wearables are not scalable would be where these remote monitoring devices would be useful.
Yeah. Okay, thanks. Yeah, maybe just a very small extension to this question is that I'm not sure when you do the clinical trial in US, do you facing an issue that the nurses, the clinicians, they do not want their workflows or behaviors to be captured by the video camera? So sometimes they're quite resistant to this technology. I'm not sure whether are you facing this issue?
Yeah, and I think this is a great question if you are attending the poster session, to also ask the students, because they're working side by side with the medical students and doctors, and can get a more candid answer to that. From my perspective, I don't hear that being, workflows are very important, and I don't think the doctors are concerned with interruptions to their workflows, meaning that they can't do their job, but they haven't voiced to me any concerns with their workflows being tracked. But it's an interesting question, and one that I haven't considered.
Yeah, thank you. So it's time to for us to continue our session on the camera PPG. And thank you again, Achyuta, for your excellent presentation. And also look forward to your new works in this area.
Thank you so much.
And also hope you enjoy our session today. Yeah, thank you.
Thank you for inviting me.
Thank you. Yeah, okay. So audience, and now we are going to our first session, the camera PPG session. Check the program. So we have, I will call your the paper title name, and then you can unmute. Maybe Daniel, you need to help a bit to unmute the author. So
yeah,
the first,
do that.
yeah. So the first presentation is the oral presentation is pruning RPPG networks towards small dense network with limited number of the training samples. So the author of this paper, could you mute? Mute.
Hello.
Yeah, I can hear you.
Thank you for invitation. Thank you for invitation. Hi everyone, my name is Cao Chen. Today I want to show you that pruning RPG network toward a small dense network with limited number of training samples. Neural network pruning reduces network complexity and strength by removing unimportant connections in the work. Few research focus on the pruning of network for RPG post-signal extraction, offset to the existing pruning research that prune large network. RPG networks are relatively small. It's interesting to see how it behaves when the pruning is applied. Under these circumstances, we investigate the behavior of common pruning techniques when applied to an existing RPG network. We refer to network architecture of FaceNet 3D CN as shown in Fig 2, and Table 1 is the FaceNet architectural specification. Pruning rate decay means that pruning rate decays gradually to the target specificity rather than only once. The drop criterion is to reset the partial weight to 0 according to the weight and the pruning rate. Regeneration refers to regenerating partial trim connection according to grading size. The formula is not expanded due to time. We use the pure data to test for experiment. SNR and flow pulse are used to evaluate performance. In this paper, the pruning method we propose is during train pruning. We prune very 300 iterations, and we use uniform distribution to keep the method simple. The base and batch numerous layers are kept dense. To begin with, the results of dense to sparse train and sparse to sparse train are shown in Table 2. The results show that dense initialization generally performs better than sparse initialization. Then we connect the best performing components together obtained in the previous experiments with RM to find the best combination. The results show that SNR increase as HF decrease. In order to show the relationship more intuitively, we plot in Figure 5 the mean SNR, a function of SF comparing with and without pruning rate decay. We found that when pruning rate decay is added, SNR with large SF decrease, while SNR with small SF increase. This can be explained by the fact that when SF is large, the network is close to dense. Adding decay introduces additional perturbation. However, when SF is small, the network is very sparse. If decay is not added, a lot of connection will be lost at the beginning of train, which is detrimental to final performance. Finally, we accumulate all the flow pulse in various iterations. The results are given in Table 4. The results show that for both dense to sparse and sparse to sparse train, the flow pulse needed is 1 order of magnitude less than that of density model. Train with decay needs more flow pulse than that without decay. For the same final sparsity, dense initialization needs more flow pulse than sparse initialization. This paper introduced pruning techniques that are currently actively researched in RPG network work, observes network behavior and derive some rules. The results show that pruning rate decay is beneficial for performance improvement, while connection regeneration is detrimental. Given the same final sparsity, dense initialization usually performs better than sparse initialization. The network seems insensitive to initial sparsity. This is my work. Thank you for listening.
Yeah, thank you. Thank you for the presentation. Yes. So the next presentation is a remote pulse estimation in the presence of face masks. So the authors to raise your hand or mute. Okay.
Can everyone hear me?
Yeah, we can hear you.
Okay. My name is Jeremy Smith. I'm from University of Notre Dame, and I'll be presenting on RPPG with face masks. Even in the presence of motion, illumination, noise. So we have methods that work quite well. And in this example, it's deception detection physiological monitoring, which is a large losslessly compressed data set. And this is an RPNet model. However, more recently, face masks have become quite common. So the main questions we wanted to ask and answer are how do current RPPG algorithms perform out of the box when we just test them on masked data? And then how can we potentially modify these models easily to perform better in this case? So we collected a data set with over 50 subjects called MPM. And this is all losslessly compressed. And both of these data sets are publicly available. So to answer the first question, if you apply these RPPG algorithms to the masked face data sets, you see some degradation as we can expect. So on the left is DDPM. If you look at like the deep learning models on the bottom, we see mean absolute error of around 2 beats per minute, which is quite good. But if we go over to the masked data set, we see an increase in that mean absolute error. So for the deep learning models on the bottom there, the error rate's almost double and more than double in some cases. And for the more handcrafted methods, we see an even worse degradation. So how can we potentially modify this and improve these methods without adding masked data to the training? And the way we actually do this is by adding synthetic face masks, which is really quite easy. If you have the face landmarks, you can just sort of crop out this region. And hopefully this will guide the model towards estimating the pulse only from the periocular and forehead regions. So we did 2 different kinds of masks. One of them, we just zero out all the pixels. And the other one, we actually get textures from a data set and create these synthetic pattern masks. We also tried a couple different landmarkers, since with face masks, the landmarking also degrades. And I'll show an example of that later. And then we trained 2 different spatial temporal models, the 3D CNN, which is PhysNet, and then RPNet, which is a model that we have. And then we reserve the masked data set just for testing. So if you look at the bottom rows here, on the left, you see a slight degradation in the unmasked testing data, which we can expect because the model is not trained at all to look at the lower face, but this degradation is pretty small. And then in the bottom row on the right for the testing on the masked data, we see a slight performance improvement when we train with this synthetic masked data. And if we actually look at, say, the class activation maps, we can see that the models actually focus more and our synthetic training works. So the left column here is training a 3D CNN without the synthetic masks. And you can see that heat map sort of covers the entire face, even if you're testing on NPM. And then in the right column, this is a model trained with the synthetic masks. And you can see that the activations are much more densely clustered and actually focus quite closely in the periocular region. And on the right, you can see that face landmarking is actually quite a bit more difficult with face masks, especially if the masks add sort of spatial textures and features. So that definitely improves or increases the errors as well. So to conclude, as we could expect, there's a drop in signal quality with face masks. You have a decreased number of pixels that you can work with. But at least practically, the mean absolute errors don't jump up too much. Of course, this is application dependent, but they're probably still usable. And then an interesting thing is the periocular region is definitely feasible for pulse estimation. So you could imagine other applications where you have videos specifically looking at the iris or pupil, and you could use the surrounding periocular region to extract a pulse. And then these synthetic occlusions guide the models to look higher up on the face and not use this masked information. Thank you.
Yeah, thank you. Thank you for your talk. So the third presentation is the remote heart rate estimation by signal quality attention network. Yeah, you can unmute and share your screen with us.
Hi everyone. My name is Haoyuan Gao. I'm a student in Anhui University. Today I will share my research, remote heart rate estimation by signal quality attention network. Remote photoplasmography has meaningful achievement to estimate heart rate. heart rate variability, blood pressure, respiratory rate, and so on. But the motion and illumination noise in natural environment is hard to remove. A high quality and low quality mixed signal are commonly. Last year, we proposed the LSTM-based signal quality assessment network to distinguish the high quality segment and the low quality segment. In today's research, our motivation is that the proposed algorithm pays more attention to the heart rate estimated from the segment, the high quality segment, and ignores the segment which is corrupted by the noise. The first proposed algorithm, LSTM-IPPG, is a many-to-many RNN architecture. Every input sample point has a heart rate output. The result of the prediction is showed. The black line is the predicted heart rate from the LSTM model, and the red line is the ground truth from the contact PPG signal by the affective method. The totally architecture of SQI-IPPG has 3 parts. First, LSTM-IPPG to predict the heart rate. Second, SQN to predict the quality score of the signal. Last, annotation mechanism uses software annotation recalculate the weight and the average heart rate between the time t and the time t plus n. This page shows the mean absolute error of the heart rate estimation. First 4 methods are the traditional unsupervised methods, and the last 3 are supervised deep learning methods. In the first list, the trained dataset and the test dataset are in the same dataset. Supervised learning methods have better performance, and our method are the best. In the other datasets, we use the model training in the MCAM to verify the robustness of our model in cross dataset task. The errors are worse than unsupervised learning models, but the advantage of supervised learning model is that its parameters can be optimized to achieve better performance. A summary of our work motivation. We want to pay more attention to the heart rate extracted from the high quality segment. Method. We use the 2 LSTM-based network to predict heart rate and quality score respectively. An attention mechanism calculate new heart rate using the information above. In result, our model has a better performance when the train set and the test set are in the same data set. That's all. Thank you.
Thank you. Thank you for the presentation. The next presentation is from the paper RPPG, an ultralight 3D CAN for real-time remote photoplethysmography. So the authors for this paper, you can turn on the camera and share the screen with us.
Okay.
We can hear you.
Okay, it's okay.
It's okay. You can start.
I'm going to show you what the RT-RPPG is, an ultralight 3D CNN for real-time remote photoplethysmography. So we start from the fact that usually for measuring RPPG from a video input using convolutional networks, we can either have, we can use, for example, face tracking and cropping, and then the spatiotemporal evaluation by using handcrafted temporal conversion and 2D CNN for manage the temporal parts, or 2D CNN for space and recurrent neural networks for the 3D CNN. Sorry, for the spatial part. So in this work, I will use spatiotemporal evaluation by the 3D CNN, which in the state of the art is giving already good values. So our idea is to propose baseline model in order to get the faster inference speed, right? So we will start from taking a 3D CNN baseline, and we will start decreasing the size of the input from 128 to 64, 32, 16, 8, 4, 2. And we will use the same convolutional layers for these examples. And the only difference will be in the pooling layers with the 3 of them. This way, we will be using the same architecture, and only the input size will be the major change. This way, for these 7 experiments, we use the negative Pearson's correlation, and we realized that using 8x8 input was good enough. Then we started to change the loss function for that temporal frequency-based loss function called negative Pearson correlation and signal-to-noise ratio, proposing this work. Once we realized this loss function is working pretty good, we start to change also the color input size. So sorry, the color channels, and we get that the YUV is the best configuration. Then what we call RT-RPPG is the baseline with 8x8 input size and the YUV color channel. Our architecture starts with an encoder and finalized with decoder. A series of convolutional pooling and activation functions will give us the RPPG. When we compare our method with the state of the art, for example, PhysNet, and we start to decrease the input size, then the loss function, and finally the input, the color channels, we get the RT-RPPG having a really good performance in terms of inference speed, having 2.32 milliseconds for GPU and 28.65 for CPU. And even though the heart rate metrics for PhysNet is the best one, and also signal quality metrics, our method also gives really close values, right? 3.8 to 2.9 is basically nothing. We still have the same correlation plot, the signal to noise ratio to 4.6. So it's actually really good results for us. So we compare the correlation plot of our baseline and the best configuration, and we improve the GPU and CPU inference time by 88%. Our heart rate metrics in 37%, signal to noise ratio in 7%. And if we compare the PhysNet, which is the one of the best state-of-the-art methods, with our best configuration, which is RT-RPPG, we also realize that the GPU and CPU improvement is really, really good. And the decrease of the heart rate measurements is not that much, or the signal quality. So basically, we have a really fast and real-time network, having really close values to those given by the state-of-the-art networks as PhysNet. Therefore, in this work, we propose a light 3D CNN for RPPG measurement. We have a speed response, and we can measure also heart rate, a really good quality. And as future works, we hope to use this network in near-infrared videos, datasets, and also to measure the capacity of our network in the pulse rate variability metrics. Thank you.
Yeah, thank you. Thanks. And the next presentation is a federated remote physiological measurement with imperfect data. So order for this paper, you can share a screen with us and also turn on your camera. So for the paper, federated remote physiological measurement. Oh, yeah.
Just 1 second, I'll unmute you. There we go.
Be unmuted. Okay. Yeah, we can see your screen.
You're unmuted, but we can't hear you.
So Xin Liu, we cannot hear you. I think you're unmuted, but we still cannot hear you.
Can you hear me now? I'm just, yeah, okay.
That's better, yeah.
Okay, yeah, I think my microphone has some issues, so I'm just using my laptop. 1 second. Oh, sorry.
Yeah, go ahead.
I'll just. Okay, can you see my screen?
Yes.
Okay, good. Sorry about that. Hi everyone. So I'm very happy to present our work about a very remote physiological measurement with imperfect data, and this is joint work between University of Washington and Microsoft. So just want to give everybody a slight background about what's federated learning. So federated learning essentially is a way that we can enable distributed device or decentralized device to collaboratively learn some models without data living on their device. For example, I can have my own data, and maybe other people can have their own data, and they do not need to share the raw data to the server. Instead, they could train their model on the local devices and upload the trained weights to the server. Then on the server sides, there could be an aggregation step that to combine everybody's weights together and generate an aggregated model. So so in that way, you could basically provide a privacy. It's just a privacy preserving model that could learn collaboratively, potentially from large scale models. So and in this slides, we kind of just raised 4 questions about the federated learning and remote physiological sensing in general. And the first question is federated learning really applicable in the field of RPPG, right? So does it really work? And the second question is, how could we perform the federated learning against the traditional supervised learning? Is essentially, is there any gap between the federated learning versus, let's say we take all the raw data together and train that? And the third one is, how do the noise label and the noisy data impacts the performance of federated learning? And the last one is, how could we leverage some signal quality metrics to kind of overcome the challenge from noise label and noisy data? So I'll just quickly present some results between the federated learning and traditional supervised learning. Here we use on-device network called TSCAN. Since federated learning is mainly for like on-device computation, so that's why we choose TSCAN. So on the left-hand side, we have we can see the difference between federal learning and traditional supervised learning is minimum. So we trained on a data set called ARFL and test on UBFC and MMSE. And so based on MAE and the Pearson coefficients for the heart rate estimations, and you can see the difference is really minimal. And on the next slides, we also showed how did we add noise on top of the existing data sets. So in here, we have two kind of dimensions. One is we add noise on the top of data, and the other one is we add a noise on top of labels. So we both add Gaussian noise, random Gaussian noise. So on the top hand side, so there's some Gaussian noise on the appearance. So as you can see, and with different levels. And the second row is the motion, is kind of the motion branch in our network, and the input for the motion branch is the normalized frame. Essentially, it's the difference between every two consecutive frames. And so we add a similar level of Gaussian noise, as you can see, as the noise became like 1.5, there's not too much signal over there. And so on the label side, we also add a similar noise, as you can see on the noise when the noise is equal to 4.5, the signal essentially became noise too. So on the federal learning algorithm side, we also propose a simple but effective approach to leverage the signal quality built on top of the previous slide. So for example, when we are aware of the signal quality of every signal segment, how could we leverage the signal quality to kind of really learn a better representation within the federal learning settings? So in here, I won't dive into too much details, but essentially is we could leverage the signal quality from every single client. So each client essentially means a device in the federal learning settings. So we could leverage the signal quality from each device to kind of do the aggregation instead of doing like a naive averaging for every single client. So let's say, for example, the client A could have like a way more high quality of data. And so that doing the aggregation process, we should put more weights. And for example, if the client B has worse quality of data, then we could put less quality of, less weights on the client B doing the aggregations. So in here, we just show that by doing such aggregation, like adaptive aggregation, we could see a clear benefits of that. Like, in here again, we train on ARFL, which has 25 subjects, and testing on the UBFC and MMSE, and you can see clearly there's some benefits between the fat weights that that's the method we proposed compare against the fat average. Fat average essentially is a naive averaging way, and on the right-hand side, we also see a similar trend from MMSE as well. On the noisy label, we do not see that much like benefit compared to the noisy data, but it's still there are some benefits on some. So on some level of like noise. So this actually raised an interesting question, that why the RPPG training is such robust to like noise. So we hypothesized that this noise will actually could be accessed like a regularization and doing the training. So this is an interesting question that we all can explore. It's like training with noisy labels. So to conclude this talk, and so we present the first federal learning system in this space, and we also propose a simple but effective methods to address the imperfect data settings. And so we also demonstrate federal learning can produce as good as the traditional supervised learning. And so we also proposed a way that could outperform the baseline, the FATF, within. Sorry. So within the imperfect data. So this research, we believe, will open the opportunity in the future, for more like a privacy preserving physiological sensing and also some large scale representation learning. Thank you.
Yeah, thanks. Thank you for your presentation. And then the next presentation is optimizing RPPG signal extraction by exploiting facial surface orientation. Yes. Yeah, you can. Yeah, Daniel, can you unmute the speaker?
Yep. Okay, there we go.
Can you hear me?
Yep, we can hear you.
All right, then I'll get started. Yeah, so hi everyone, I'm Kyle from HKUST, and today I'm very happy to share our work on optimizing RPPG signal extraction by exploiting facial surface orientation. So as the signal to noise ratio of the RPPG signal varies across different areas of the face, region of interest selection or ROI selection methods are a very common pre-processing technique used to minimize the effects of noise while choosing the areas that contain the most physiological information. Although many studies have used ROI selection tools to improve RPPG signal extraction, less studies have investigated the influence of the ROI's surface orientation. So according to the DRM, actually, the specular reflection and diffuse reflection strongly depend on the angle of reflection of the vectors. Therefore, we proposed a angle map representation that is a two-dimensional image containing the angle of reflection of each pixel to study the effects of the surface orientation on the extracted RPPG signal. So for each image frame, we first applied a face mesh to detect, in this case, media pipe face mesh to detect 468 3D landmarks of the subject's face. The 3D landmarks serve as these reference points for the subsequent calculation of the surface normal vectors and also the angle of reflection of the facial pixels. So to calculate the surface normal vectors, we took inspiration from Open3D, which is a modern library for 3D data processing by Intel. We define a set of possible surface normal vectors at a specific landmark, and based on this equation here, and we use the analysis of covariance, ANCOVA, to choose the most representative surface normal from this set. We then calculate the specific angle and plot out the angle map based on a basic trigonometric function. So after calculation of the surface orientation, we map the angle of reflection of each 3D landmark to the corresponding 2D location of the landmark shown here. We extrapolated the surrounding area of each landmark to generate this final angle map. The figure on the right shows how the angle map changes according to the subject's face orientation. Additionally, the right column here shows the selected area when we apply a simple 45-degree threshold. In other words, the pixels with an angle of reflection that is larger than 45 are removed. So we validated our method on the UBFC RPPG dataset, which is a pretty popular benchmark dataset in this field. We used a pixel binning technique to average out sensor noise and produce a 16 by 16 array representing individual ROIs of the face, which we call pixel ROIs in this case. The image on the left here is the average correlation between the extracted RPPG signal and the ground truth BVP signal, and the average angle of reflection on the right here for each pixel ROI over the 50 subjects in the UBFC dataset. So the eyes and lips here are masked out because we only wanted to consider the skin surface. We see that the pixel ROIs near the cheeks and the forehead actually have a higher correlation coefficient and also smaller angles of reflection. We also observe that there's as we decrease the angle of reflection, it also increases the correlation coefficient between the predicted and the ground truth signals. To further validate our hypothesis, we also perform pixel binning to produce additional pixel ROIs of different arrays, different sizes, specifically 8 by 8 and 32 by 32. And as shown on the right, we also see there's an inversely proportional relationship between the correlation coefficient and the angle of reflection, which is consistent with our previous hypothesis. So we also applied some basic thresholding to mask off pixels based on their angle of reflection, and using this as a means for ROI selection. And the two figures here actually show the average correlation coefficient between the extracted RPPG signal and the ground truth, and also the average SNR of the extracted RPPG signals at different angle thresholds. So by setting a threshold at around 45 to 50 degrees, we see that the signal extracted from the mask, regardless of the size of the pixel ROI, has a significantly higher correlation coefficient and SNR than the RPPG signal from the full face benchmark. So we hypothesized that smaller angles or a smaller angle threshold does not achieve a better signal due to some overmasking and also increasing the amount of sensor noise. So in summary, we report the first study on the effects of surface orientation on RPPG using an angle mask. Our results show that as we decrease the angle of reflection, it also significantly and linearly increases the correlation between the extracted RPPG and the BVP. We plan to take our future works into two directions. First, exploring the quality of the RPPG signal in different facial areas and of subjects facing different directions, also those undergoing head motions. And we also want to explore the use of the angle map for optimizing remote measurement of vital signs, obviously, such as utilizing it as an attention mechanism and also to support synthetic data generation. All right, thank you.
Yeah, thanks. Thank you for your presentation. Yeah, for the next one is efficient remote photoplethysmography with the temporal derivative modules and the time shift invariant loss. Yes, and so yeah, to be unmuted.
Okay, can you hear me?
Yep.
Yeah, we can hear you.
Thank you. So, hi everybody, and thanks to attend this presentation. My name is Kim Comas Martinez, and today I'm going to present our work titled Efficient Remote Photoplethysmography with Temporal Derivative Modules and Time Shift Invariant Loss. So, remote photoplethysmography has undergone a significant change in the last decade, and more specifically, deep learning-based approaches have outperformed traditional handcrafted methods, showing an impressive hair rate results. However, these deep learning approaches present some disadvantages with respect to the traditional methods in which we focus during this work. The first one is that most of the existing deep learning approaches are using 3D CNNs, which is the most common and simple way to model spatiotemporal information, but most of them are not considering the high computational cost of these architectures. And secondly, most of the available datasets are recording PPG signal from the finger, and therefore it exists a physiological delay between the PPG measure from the finger and the PPG measure from the face. This physiological delay is commonly called pulse transit time, and this pulse transit time is not affecting traditional methods, but it's affecting deep learning approaches, especially during the training process, because we are enforcing our network to learn a wrong PPG phase. So regarding the first challenge, we present a lightweight end-to-end architecture in order to model our RPPG signal in a more efficient way. For that, our architecture, it consists of a straightforward spatial encoder followed by a temporal derivative module which aggregates multiple 1D differential temporal convolutions in emulating Taylor series expansion. Regarding this temporal derivative module consists of two successive derivative convolutions, which represents the first and the second order derivatives, which is the same as the velocity and acceleration dynamics of RPPG. Regarding the differential temporal convolution, it consists of a non-trainable weights, with a predefined temporal kernel that is modeling the temporal feature difference between consecutive frames. Then, regarding our second contribution, we introduced the temporal adaptative location shift loss, that is a new temporal objective loss function that is useful to train deep learning approaches invariant to temporal offsets in ground truth data. To create this objective loss function, we impose two different assumptions. The first one is that the temporal offset should be relatively small in order of milliseconds, because otherwise it wouldn't work with existing methods. And then the second assumption is that this temporal offset should depend on the physiological status of each subject and the recording setting of each data set. Therefore, the goal of this loss function is to learn a latent distribution that depends on the all possible k offsets and all the available subjects in our training set, such that what we expect is to assign the highest probability to the k offset that gives the lowest mean square error. Then in the bottom left, we can appreciate a comparison between the standard mean square error and our proposed loss, where we can appreciate a better amplitude prediction invariant to this temporal offset. And finally, on the right, we can see the learned offset distribution for the pure dataset, in which we can see the probabilities of the optimal temporal offset for all the different subjects. Then, in terms of results, we compare our method with the existing approaches using two public datasets, pure and UBFS dataset. And we have used the typical heart rate metrics such as the mean absolute error, the root mean square error, and the Pearson correlation coefficient, as well as some performance specifications such as the number of parameters and multiply accumulate operations, as you can see on the right. From the results, what we can see is that our approach is able to reach the state of the art in terms of heart rate estimation accuracy, dealing with a much lower number of parameters and lower computational cost. So in conclusion, we present in this work a novel lightweight architecture to address the efficient modeling of RPPG dynamics by aggregating this concept of differential temporal convolutions. Also, we introduce a new temporal objective loss function called TALOS that is able to learn the latent offset probabilities of the ground truth data. And finally, our future work will focus in exploring the combination of higher order dynamics to improve the temporal modeling for RPPG estimation. So that's all, and thank you very much for paying attention.
Thank you. Give a presentation. And the next presentation is perfusion assessment via local remote photoplethysmography. Yes, and yeah, Daniel, you need to unmute Benjamin. Thank you.
Okay, I hope you can hear me.
Yeah,
we can share your screen with us.
Okay.
Yeah, we can see your screen.
Great. Yes, hello everyone. My name is Benjamin. I'm from the Fraunhofer HHI in Berlin. And yeah, just a short disclaimer. The presentation contains some images where you can see blood and videos and different human tissue. I made it as family friendly as possible, but yeah, I hope it worked. And if not, just pretend what you are seeing is synthetic data. So yes, so the goal of our work is we want to assess the perfusion of human visual human tissue from RGB video recordings. So is this tissue sufficiently supplied with blood? And in our paper, we apply this assessment in the medical field, where we analyze the perfusion of newly implanted skin and organs, and in the security system, where we want to detect presentation in text. So here we see a typical RPPG principle from a video showing our region of interest. We extract an RGB signal, and then we apply the plane orthogonal to skin transformation and get our RPPG signal. And then we perform our tissue analysis on this signal. And this analysis is based on 4 parameters: the pulse rate, which we extract from after applying a Fourier transformation in the frequency domain. Then we calculate the so-called perfusion index. This is calculated from the green color channel as a ratio of the pulsatile blood flow component, so the AC part of the signal, and then the non-pulsatile static blood flow, so the DC part of the signal. And this index is a good indicator of the pulse strength and of the analyzed position. We also use the signal to noise ratio to quantify the signal quality. And the 4th parameter is, which we call reference correlation coefficient. So this image here, it shows a view during the implantation of a skin flap into the oral cavity. And we mark here then the region of interest, which is this implanted skin, and the reference region on the cheeks of the patient. And then we calculate the correlation between the RPPG signal of both regions, and this parameter we use then later for our analysis. Yes. So here I want to show you a couple of results from our medical application. The video in the lower part will show newly implanted skin flap into the oral cavity, and the skin is implanted from the forearm of a patient, and then there's defect reconstruction in the mouth. And at some point, the physician is opening the arteries, and blood will flow into this newly implanted skin flap. And here we visualized 2 of our parameters with the heat map. So blue is a small value and red is a high value. Yes, and then by that we can analyze how sufficiently supplied is this flap with blood. But first have a look at the plots in the top of the slide. So this is our global analysis. Global means in this case that we calculate 1 RPPG signal for the whole region of interest. And in total, we recorded 14 patients, and these plots show the resulting perfusion index here on the left, and on the right, the correlation reference. And after opening the arteries, the perfusion index reaches here a peak, and then it lowers and reaches a steady level. And the reference correlation also increases after the opening of the arteries, and then it stays at a high level. Yes, and in the lower part, you can see the same behavior locally analyzed, and as here shown in the global plots. And the waveform I showed you here in these plots, we could see these waveforms for 13 out of our 14 patients. One patient, the patient 8 here in red, both parameters showed kind of an abnormal waveform, so no peak in the perfusion index and no increase in the reference correlation. And this odd behavior was confirmed later, five weeks after the implantation. This flap became necrotic and has to be removed again. And with the help of our analysis, the physician could already see that something is wrong just 2 minutes after the reperfusion, and he had not to wait 5 weeks. So that would be a great increase in performance for the whole procedure if the physician would have kind of an analysis right away in the operation room. So we also used our perfusion assessment to detect masks in security applications, or respectively, we can detect living skin tissue, also here locally analyzed, so pixel-wise analyzed. For example, here the person here is wearing a face mask, and here the magnitude and signal to noise ratio and reference correlation. No increased values are visible. Here the person is wearing no mask, and we have large values, so it is easy to detect if the person is wearing some kind of mask. We made the same with partial mask on the cheeks or on the nose, and also this mask could be detected with our local analysis. So let me quickly conclude. Yes, we presented a reliable method for RPPG-based perfusion assessment. The method achieves objective and reproducible results. And also these results were verified by medical expert. Yes, also the application, you can apply this analysis in multiple areas, as well as we tried it for kidney transplantation. And that would be also a great tool for the physicians there. And also presentation attacks with partial and full facial mask could we easily detect. Yes, that was from my side. Thank you for your attention. Have a look in our paper for more details. And yeah, nice workshop.
Yeah,
bye-bye.
Thank you. Thank you for your presentation. And the next presentation is gated recurrent unit-based RNNs for remote photoplethysmography signal segmentation. So the authors of this paper, yeah, you can turn on the camera. Yeah.
Rita, we could hear you just a second ago, but yeah, if you could unmute, that's great.
Hello, can you hear me?
Yeah.
Oh, cool. So, hello everyone. I'm going to present my paper, which was titled Gated Recurrent Unit-Based RNN for Remote Photoplethysmography Signal Segmentation. So to introduce this work, well, in a previous study, we had to remove a certain number of RPPG signals because they contained great portions of noise, which was induced by motion. So it raised a question, which is how to define reliable portions of RPPG signals when either ground truth is unreliable itself, or when we don't have any ground truth. For this, we propose to use a recurrent model to segment RPPG signals. So the method followed included 4 steps. First step was data acquisition. So we collected 11 RPPG and ECG signals from PhD students. Participants were seated in front of the camera and were able to either work or discuss. ECG signals were acquired using the polar H10 belt, and the RPPG signals were estimated following a classic pipeline using the POSE algorithm. The next step was data labeling. So for this, ECG signals served as ground truth, and the labeling was made based on ECG peak occurrence times. So ECG and RPPG peak occurrence times were compared, and this allowed us to do a first RPPG peak labeling, as you can see in the figure. Then we made a visual inspection, so we could correct mislabeled peaks, as you can see in the bottom left figure. And next, we developed an algorithm that allowed us to label the whole section, the whole RPPG section, so to transform the peaks, the peak labels into sample labels, as you can see in the bottom right figure. The third step was apply a data augmentation process. For this, the RPPG collected the segments, once labeled, were partitioned into small portions, so of 1 minute, 20 seconds, and 30 seconds, and an algorithm that allowed fusion between 2 different sections was developed. Sorry. So the 3 figures show the main steps followed in this algorithm. So first, given 2 sections, their borders are compared. Then one section is fused with the other section based on their values, the border values. And the final result is given by the bottom right figure. As you can see, this is the resulting new section, new RPPG6 section. So here we have examples of generated signals following our data augmentation method. I'm sorry. Yeah, and here we have the final step of our method, which was defining our RNN method, model. We called it 1DCNN plus BGRU model. So the input was either time sequence, RPPG time sequences, or time frequency sequences, which were obtained using the Fourier synchro-squeezed transform, or a combination of time and time frequency sequences. The first main layer of this model is a unidimensional CNN that will compute local features along the signals. Then the second main layer is a bidirectional GRU, which will compute outputs for each sample based on past and future inputs. And finally, a sigmoid function will give a probability for each RPPG signals for being either reliable or unreliable in order to constitute reliable or unreliable portions. So the results obtained are an accuracy rate of 86, of nearly 86%, using time sequences. And here we have the confusion matrix, which gives the sensitivity and the specificity rates. And here we have an example of label predictions using our model. So on the right, we have the true labels of a signal from the test set, and on the right, we have the predicted labels. So to conclude, we present in our article, in our paper, method to an RNN model to segment RPPG signals and define noisy and reliable portions. But this study constitutes a preliminary study that should be completed with either more complex models or include other methods for data augmentation, such as adding a Gaussian noise, for example. And why not try to use it for a real-time algorithm to be able to define a noisy portion of an RPPG signal in real time. Well, that's it. So thank you very much for your attention. I don't have to stop the.
You can just stop sharing your screen when you're ready.
Can you hear me?
Yep. And the next paper. Oh,
yeah. Sorry, my network is a bit unstable. Just go ahead.
The next paper is deep learning classifier for advancing video monitoring of atrial fibrillation. And yeah, please go ahead with your presentation. Thank you.
Hi, everyone. I am Camille. I am gonna present. I am going to present deep learning classifier for advancing video monitoring of atrial fibrillation. What is atrial fibrillation? Atrial fibrillation is the most common type of heart disease that causes irregular heartbeat, rapid heartbeat, and because of that, that causes the blood clots, risk of stroke, heart failure, heart-related complications. And on the right figure, you can see on the left side, we have a normal heart. And on the right side, we have a AF heart. And on the bottom of the figure, you can see normal heartbeat is the regularity between each heartbeat. The distance is similar, but for irregular heartbeat, the distance is different. And because of that, and there are some treatments that can be temporary applied to the patient, like reset the heart rhythm and rate, control heart rate, or prevent the blood clots. However, these treatments are temporary. Because of that, the patient needs to go to hospital periodically for screening. And in 2017, you can see like 37 million cases happened because of AF, and 300,000 cases, death cases happened because of AF. And we believe that since AF is a dangerous heart disease, and there are some risks, because of that, we believe there should be a way to increase the monitoring time, not only hospital and outside of the hospital. That's why we want to implement an approach that can be easy to implement and can be cost efficient to apply to any device, and can be sensor agnostic. This will make it more generalized. And we want also high accuracy for detection of AF. On the right figure, you can see like the patient, if we achieve that goal, the patient can be monitored passively at home or hospital. And after, if there is a problem, then actively he can be monitored also. And when he is actively monitored, when there is a problem, he can go to hospital, and by using ECG, we can accurately detect if the patient has a problem. If there is a problem, the patient can go over a treatment, and after this monitoring cycle can repeat again. In our proposed approach, we used a deep learning approach that can be applicable to various biological signals like ECG, PPG, and we used two different kinds of VPG. One was high quality camera, one was low quality camera. What we did, we obtained our data, and we split that with 25-second data blocks. And after we apply some pre-processing like bandpass filter, and after we apply some CNN layers to that data, and after we drop out layers, and after that we apply the max pooling, and at the end we apply a fully connected layer, and we get from that fully connected layer one binary result that will show us if the patient is AF or not AF. On the other hand, for comparison, we try to find IBIs or RR intervals for ECG and other kind of signal to be able to compare our result with the classical approaches. And for ECG, we use a Penn-Tompkins with some filters to find the peaks. On the right side figure, you can see we accurately be able to find the peaks, and from that we calculate RR intervals. And for PPG, VPG 180 and VPG 30 Hz, we also apply butter bandpass filter with some other kind of filters. And at the end, we find the peaks for each of them. On the right figure, you can see. And after that, we calculate IBIs from that. And by using these RR intervals and IBIs, we calculate the features that is shown on the table, like SDNN, RMSSD, PNN50, that are classical features, and also SVD, entropy, and IQR. By experimenting that, we see that they are giving valuable information. And what we did, we used each individual feature like SDNN, RMSSD, and PNN50 with basic thresholding classifier, which use only one feature. And after we use the combination of them with the support vector machine, and also we used all the features that we gathered and used support vector machine to detect the AF. And overall, we have three different kind of classifier. That one was basic thresholding, and the other one was support vector machine, and the other one, our proposed approach, is CNN. And our sample size was 2,684 for each of them, and 80% data we used for the training. And for basic thresholding and SVM, we used 20% of the data for testing. But for our proposed approach, we used 10% of the test data for cross validation. while the training was going on, and 10% of data we use for testing. For BTC, normally we are using only one feature, since it is finding only the threshold, and left side is like AF, right side is non-AF. But for SVM, we use 26 features for the by combining the old features, we use 26 features. And for CNN, we use our raw data, just we apply some simple pre-processing, and then we feed that to our model. In our clinical study is conducted in a hospital, and we use like on this schematic description, you can see we use like 4 different kind of sensor that I showed you, like ECG, PPG, and 2 different kind of VPG sensors. And we applied that experiment to 46 subjects. And for each subject, they were, we recorded 5 minutes, 30-second data from them before they had a problem with their heart. And after the treatment, their heart become normal, their heart rate become normal. We again measure 5 minutes, 30 seconds data from that. And this was a controllable environment. And because of that, there were less noise about the movement. And also light was stable. And this is our result for all the classifier that we applied. As you can see, like from the table, the important part for us was find a way to get from the sensor high accuracy and stable result. And you can see for CNN, we have a high accuracy, but for others, some of them working well, like for ECG, we can see like BTC, PNN50 is working well for ECG. However, like for other result, for PPG and VPG, we cannot see the same result. And in conclusion, our proposed approach works well on ECG, PPG, and VPG with high accuracy. And because of that, we are able to actually, we believe we will be able to like achieve more, full monitoring cycle that can not be only in the hospital, but home or any other kind of places. Also, since we are using VPG, passive monitoring is possible, and actually that makes it more usable. And also, this data, as I said before, is gathered like in a highly controllable environment. Because of that, in future work, actually, we want to improve our model that can be worked in uncontrollable settings. Thank you.
Yes, thank you. Thank you for your presentation. So it's the group Q&A session. Yeah, and so anyone have questions, you can put your question in the chat.
I'm going to invite all of the authors to unmute. So just be aware of that. So I go through the list and invite you to unmute.
Yeah, since Kamya, you are the last presenter, I have a question regarding this atrial fibrillation study.
Mm-hmm.
Yeah, and so I would like to know that did you compare the physiology of these 2 signals, like contact PPG and the camera PPG, yes, to see if we just obtain the PPG signal, the rest of things are all the same, or do they still give different features in terms of the atrial fibrillation?
Yeah, actually, like when I was applying, like the difference part for each signal was pre-processing part, because pre-processing is depend also the signal like frequency, high frequency, low frequency, this kind of things. That's why ECG I apply totally different pre-processing than PPG and ECG. But overall, at the end, for the classical approaches, I just find IBI and RR intervals. But for deep learning approach, since I have a raw data, we believe that overall we have at the same data point that is referring to the heart variability that shows the AF or non-AF. Because of that, only in my feature, the input layer, when I am feeding the data, the input layer dimension is changing. But overall, after that, when I am feeding the CNN, I am feeding the same feature dimension with different data points. But overall, they are going through the same structure. Is that was answer for your question?
Yeah. Okay. Yeah, thanks. Yeah, I see there are also already 2 questions in the chat. Yeah, maybe for the author, Kyla. So Daniel has a question regarding your efficient remote PPG with temporal derivative modules, this paper. Can you address this question?
Yes. Can you hear me?
Yep.
Yeah.
Yeah. So yeah, this is actually a good question. Well, in the assumptions, we are assuming 2 different assumptions, but maybe this can be another assumption, a third assumption, because it can be possible to be increase the heart rate during some drive, but we are assuming that this physiological status of the subject it's the same. So if we are increasing the heart rate in the finger, in the face, it should be also increased. And therefore, we are assuming that this change always is in the same way for both cases. But of course, we need to continue study this, because maybe this cannot be true. But yes, of course, is a first assumption, because it's a difficult problem, because actually we don't know the real solution for this temporal offset, and for the reason it's complicated to solve this kind of problem.
Yeah, thanks. Yeah, maybe also a small extension to that question is that if you can capture the PTT, actually PTT has a correlation somehow with the systolic and diastolic blood pressure. Maybe I don't know if you can try to calculate PTT and use the network to learn that, to predict the blood pressure thing.
We don't consider this option, but maybe as future work could be interesting to look at that. Yeah.
And the other question is for Xin Liu for your paper fat rate learning.
Yeah.
Could you address this question?
Yeah. Hi, Jeremy. So thanks for your question. So in our paper, we treat each subject as a client. So during the training, we did use all the subjects. So for the first part of the question, yes. If you ask if we test on all the subjects, yes, too. So we trained on the federal learning ways in our training data set. So our training data set includes 25 subjects, and we treat each subject as a client. And so we basically aggregate those 25 subjects during the training, and doing the testing, we kind of just do as a similar way as the traditional supervised training. So we test on all the subjects on MMC and UPFC. And for the second part of the question, did we allow for more weights from the specific users? Yes. When we simulate, like for example, different noise levels, we actually assign different noise weights to different subjects. So doing the training, so when we were assigning higher weights on certain subjects, we did put more weights to the aggregation on specific users. Did I answer your question?
Yeah, that answers the question. I guess I was curious, and maybe this is for a future paper, if you could sort of have some subjects that are also in the test set and the training set, such that each model could be tested with, rather than having a single model for testing on all subjects, you could have like more personalized models per subjects. So sort of combining the weights on the server also with a little bit of training data from each client to have a more personalized model. That's what I was curious about.
Yeah, that's a great point. Yeah, thanks for this question.
Thank you.
Yeah, and also, Xin Liu, I also have a small question for your presentation. is that I see that you use the Gaussian noise as a typical noise to simulate data. But the Gaussian noise is just the one type of noise that is representative for the sensor noise. Did you try other noises, like for example, the lighting variations, more physical noises?
Yeah, that's something actually we're currently also actively working on. So the noise you mentioned are more like a real world noise, right? Lighting and motion artifacts, and also could be like, you know, background noise, something like that. So right, so this is a very good point, and it could be an next paper for the federal learning. Yeah, thanks for this question.
Yeah, thanks. And the other question is for the paper remote pulse estimation in presence of face masks. So can you address this question?
Yeah, so they're asking about in activation maps, there's actually pretty strong activations around the eyes, specifically like in the inner eye here. And we found this interesting as well. So there's a couple things here. First is that I wouldn't necessarily use the class activation maps as like an end-all be-all and perfect representation at what the model is using, because we're just sort of looking at, you know, one of the last couple layers. So at that point in the model, it's using that information. But if that is very salient for the model, it could have some physiological explanations as well. So I know there's the ophthalmic artery that goes up sort of next to the nose here through here. And then the canthe, which is like the inner and outer part of the eye here. It's possible that there could be a strong pulse signal in those locations. So that could be another explanation as well.
Yeah, okay, thanks. Did that address your question? Okay, and we have the other question for the paper optimizing RPPG signal extraction. Could you answer this question, author? How computationally expensive is the computation of the surface normals?
Yeah, so in short, we tried it, and in our test, it was actually quite quick, because in order to determine the facial key points and also map the surface normals, we did use some elements of deep learning as well to get the facial key points, and it was more of a lightweight network. So the short answer is yes, it is possible to implement in real time, but we do want to do a little bit more work there to see exactly how fast it can go.
And so can these normals be used for other, like a vital signs measurement, like a motion or the BCG motion or other things?
In terms of BCG, we haven't thought that far yet, but as a means or as another feature for neural networks, or as a potential attention mechanism, or even to support synthetic data, I think, or we think there's definitely room to fit that in there.
Yeah. Okay. I think that's good for the time. So now we will have a 15 minutes coffee break. And after that, we will have the 2 sessions, the blood pressure and activity monitoring session, also with a very nice keynote from Ashok. So yeah, just have a rest and see you in 15 minutes.
Yeah, we'll start the next presentation at 11:35 Central Daylight Time. So, yep. Great. Thank you, everyone. Thank you to all the presenters, all the authors. Great session. And to our keynote speaker as well, Ashuta. Thank you.
Hi, Dan. Thank you. Can you hear me?
I can hear you. Yeah, sorry, I was on mute. Do you want to try sharing your screen?
Yeah, so it's the other. I think somebody's okay.
Yeah.
Let me try now.
That looks good.
Okay, wonderful. I think we're all set. As long as you can hear me well, I think we're all set. I'll just enable video so you can see me as well. It's just that suddenly my the audio on my laptop started behaving weirdly, and so it's just safer to use the audio on my iPad.
Yep, it looks good. I can hear you. I can see the slides. I can't see your video. But that's the only thing.
Oh, that's the physical. I enabled it digitally, but did not physically open the camera.
Oh, okay, got it.
Yeah, now you should be able to see the video as well, correct?
No, not yet.
Are you sure?
I still see your avatar. Oh no, I can see your video. Yeah, sorry, you've got two because you've got two.
Yeah, because I've got two. Yeah,
got it. Okay, yeah, I can see your video. Sorry, I was looking at the wrong screen. Yeah. Okay, great. Yeah, so if you just want to
I'll just hang on here. I'll leave the first I'll leave the first slide on like this, if you don't mind, and then whenever
that's fine.
You can just get started.
Great. Cool.
Sounds good. How are you doing, Dan?
I'm good. Yeah. How are you?
Good. This was a very nice session. I really enjoyed it. I couldn't attend the first 15 minutes of Achyuta's talk, but I joined in about 15 minutes late. But after that, it's been really nice. Thank you for organizing this, you and Venjan, and yeah.
Yeah, no, it's great. Yeah, I think we had 50 or 60.
Thank you, Ashok, for giving us a talk.
Oh, my pleasure. Thank you for inviting me. I was hoping to attend CVPR in person. Are either of you attending in person?
Yeah. No.
No. Unfortunately, yeah, still getting used to the idea of these big conferences in person. Honestly, yeah.
Yeah, I was thinking about it, and then eventually, finally, I have some international travel coming up next week. So I said, well, let's just stay put for now.
Yeah, it's a bit risky still to,
Yeah. This seems to be really, this is a really active area. There's a lot of work going on here right now. It's amazing how quickly the area is growing, right?
Yeah. No, it is, and yeah, I see. I mean, I see startups every couple of weeks. Different startup, and yeah, it's kind of exciting to see some of the technology get kind of closer to FDA approval and stuff like that. So, or like at least different types of classification, kind of regulatory stuff. So, as well as the research, yeah. Oh yeah, I'm looking forward to your talk because I don't think I've ever kind of heard about all of the different things your lab's doing.
Oh, okay. This is I thought a little bit about it, and I realized that a large portion of today's workshop is going to be ultra focused on RPPG, and so I didn't want to spend another hour. So I decided I was going to talk a little bit broader about the expeditions project we have ongoing and some of the results from that project.
That's great.
I think it'll be very well connected, but it'll be slightly different. And hopefully this is something that gives the audience as well a little bit of freshness as well. We'll see.
actually, we already planned to invite you to give us a talk even in the last year, but yeah.
Yeah, last year. Yeah. I didn't. The last 2 years have been a blur for all of us, hasn't it?
Yeah.
Yeah, yeah, indeed.
Hopefully next year is going to be much better.
Yeah. Yeah.
Feel like that's what I said last year too.
Yeah. And Eva is also your student, right?
Oh yes,
she's
Eva.
Yeah, she's quite involved with us in early years, like
yeah,
in this session. Yeah.
And Eva was my student, but also worked really closely with Dan as well. I think half of Eva's work in at least the PPG remote monitoring area is with Dan. So Dan was a significant influence on Eva's PhD as well.
Yeah, great collaboration. Have you got any students taking over that work?
Not this year. I will be hiring somebody who will likely take over that work. Right now, I do have a project looking at perfusion in anastomosis. So like these vascular surgeries that are, so we're looking at during vascular surgeries after the, so let's say whether it's a blood vessel or it's the intestines, which for the most part is just blood vessels. Both the two big surgeries are gastrointestinal surgeries and kidney surgeries, where transplants, where you need to reconnect blood vessels and you need to make sure that there's sufficient perfusion. And so we have a project ongoing where we're trying to use image-based techniques for remote perfusion measurements in the field. We'll see how that goes. I mean, it's early days, but we need to hire somebody to take that forward.
Oh, that's great. Yeah. That was so let me just double check. So Benjamin's presentation kind of related to that, right?
Yeah, that's correct. Yeah, Benjamin's presentation was related to that. And also, yeah.
You're also running the clinical trials in US for this this topic. Yeah. I'm also working on the clinical trials here in China. Yeah.
Oh,
like
okay.
To organize these multi-center hospital studies, but now it's focused on more on the ICU and the NICU, the NICU.
Okay.
Setting.
Okay. What kind of what are you looking for in the NICU? I can imagine there's really a lot of potential because they just don't like leads at all. So any leads that you get rid of is really useful in the NICU.
Yeah, for NICU. For ICU, are more looking for those like a deteriorated patient because there are like lots of desaturation and a high blood pressure, and use that to validate the sensitivity of this measurement. But later we want to use in these not really use in ICU, but the verifying ICU and then use for the HDU, a high dependency unit. Yeah, well, patients are not closely monitored with this monitoring device. But yeah, then a camera could be.
We have been looking at blood pressure as well, but it looks like the methods for remote blood pressure measurement, not even remote, but even like PPG based blood pressure measurement, they're not very robust right now. They are still early days, so it's not something that can be used at all.
You know this Makumana? Do you know the Makumana?
Who?
Makumala. Professor
Yes, Mukamala. Yeah, Ramakrishnan Mukamala.
Yeah, we write a chapter on this book chapter on the camera blood pressure. Yeah, we think that for measurement, the trend is somehow okay, but the problem is still the calibration.
Yeah, I mean for personalization, I think for personalization, I think there is still hope. But for the non-personalization version, meaning you can enroll a new patient, and for the new patient, you can estimate blood pressure. It still seems really early days. It doesn't look like many of these, while there are many works, it doesn't look like they actually do much right now. Right?
Yeah, I think the post if you're basing it on post-wave velocity, post-wave analysis, like I think there's a lot of challenges, even with calibration, still, in my opinion. Yeah, but with multimodal, I think there's a lot more potential. So whether it's combining, BCG or maybe audio, cardiac movements plus video.
I mean,
maybe
Venjan was mentioning Ramakrishna Mukkamala's work. So he, for example, uses like a pressure sensor, primarily as a signal quality metric, and I think that's like starting to be multimodal in that sense.
Yeah. I think that works really interesting. Yeah.
Everyone network is a bit worse. The calibration is still an issue for the blood pressure. We have written a book chapter on that. To measure the blood pressure change, the trend is somehow okay. Like we also used ice water stimulation and these protocols to verify the trends. But for per subject calibration, it's pretty difficult. Yeah.
Okay.
Great. Well, I think we'll get started in just a minute. So everyone on the call, if you want to kind of come back, if you can hear me. So welcome back to the workshop. So this next half of the workshop, we have another keynote speaker. And I'll be introducing our speaker in just a second. And then we have two paper sessions, the first of which is looking at blood pressure, the topic we were just discussing. And then the second session looking at camera-based activity monitoring. And then we'll have a wrap up towards the end of the session. So hope you all had a good coffee break, and thanks again for the really engaging session this morning. And I'd like to introduce our next keynote speaker. Ashok is a professor of electrical and computer engineering at Rice University. He received his PhD from the Department of Electrical and Computer Engineering, the University of Maryland. He has a great portfolio of work in computational imaging, much of which is applied to health sensing. And today he'll be presenting on his work with a large project looking at imaging methods for seeing below the skin. He's also been a co-developer of technology that has been spun out of the university, including FlatCam, a thin sensor chip that for lensless imaging, and has received large grants from DARPA, amongst other bodies, for his research, and it currently has collaborations with other universities developing optical hardware and software interfaces, again, much of which is aimed at health sensing. So we're delighted to have you here, and we'll pass over to you, Ashok. Ashok, we've lost your audio, I think.
No, we cannot hear you.
Yeah, we can't hear you, Ashok. We could just now. It just seems to we've seemed to have lost it. We can see your screen fine. It's just the audio. Oh, sorry.
Yeah, maybe
Again, you had I think we can hear you now. Yeah, sorry. Ashok,
Don't worry. Hopefully you can hear me now.
So, yeah, we can hear you now.
Thank you, everybody. Thank you, first of all, for inviting me to this workshop. I'm delighted to be here. Today, I'll be talking a little bit about seeing below the skin for next generation wearables. Before I start, I'll start with a short apology, just in case I am recovering from a viral infection. Apparently, there are other things that are not COVID going around as well. And so I might cough occasionally. If I do, please ignore them for the time being. Thank you again. So today I'll be talking about this large project that we have. This is a project involving many universities, Rice, Carnegie Mellon, Cornell, CMU, Yale, and MIT. And our goal is to build the next generation wearable and implantable systems with the goal of using light to see below the skin. And so I'll tell you a little bit about the progress we've made in this direction. It's early days yet. What is the primary goal here? The primary goal here is to be able to image at cellular resolution or near cellular resolution beneath the layers of skin and tissue that we have on the human body. What is the current limitation in terms of depth and resolution? On the right-hand side is basically a plot of all the existing techniques for imaging. And on the x-axis of this plot is the spatial resolution that this imaging technology can achieve. On the y-axis of this plot is the depth of penetration at which that imaging resolution can be achieved. If you look at conventional optical methods, that's basically this green dotted lines there. So epifluorescence microscope, confocal microscope, multiphoton microscopy, they're all on that line. You see optical coherence tomography reaching close to the ballistic imaging limit, but at really very low depths of penetration. And then you have on the right-hand side, the border is given by the photoacoustic tomography limit. Essentially using the fact that your cells and molecules in the human body do respond to audio. So if you hit it with light, which has been acoustically modulated, then these cells absorb this energy and send out audio or audio energy that can then be sensed without scattering. So the question is, can we use these technologies somehow to do what we like to call computational photoscatterography? That is, when photons pass through the human body, these multiply scattered photons, they contain information about scattering tissues. Unfortunately, this information is all jumbled up because the location of these photons is no longer, the direction of each of these photons has been completely altered due to scattering. Can we build imaging instruments that capture multiple dimensions of light and corresponding inverse scattering algorithms that will allow us to extract this information and surpass the depth imaging limit? What's the opportunity here? What are we excited by? We are excited by the fact that light travels deep inside the human body. I mean, centimeters deep inside the human body. The human body, for the most part, is a heavy forward scatterer with very little absorption, especially in the visible wave band. There is absorption, of course. We know that blood is red. We know that and therefore it absorbs green light and so on. But for the most part, the human body is an incredibly is a scatterer, and therefore you can send light from one side of the human body to the other. For example, here is an image where the only illumination is from the other side. And so even though you do not see much light, the only light that you see is light that has gone through my hand to come out on the other side. And you can still see that there's a fair bit of light energy that does come out. Light, especially in the visible wavelengths, is just non-ionizing at the kind of powers that we are talking about, which is incredible because then it really becomes a safe technology. currently both illumination sources and detectors for visible waveband especially is just really inexpensive to produce, to control, to mass manufacture, to distribute. And so one could imagine a new era of devices that are both safe and can also be personalized, meaning all of us can have these devices at home to monitor our own health status. This would be like having an X-ray at home, which you don't want to do right now because X-rays are ionizing and therefore not safe for continuous monitoring purposes. What's the challenge here? The challenge is simply light scattering through skin. So photons are scattered by human tissue. And the mean scattering length in human tissue is of the order of 100 micron, which means there's an average of 10 scattering events per millimeter of tissue. Average thickness, you want to image 5 centimeters deep into the body, let's say the abdomen, then we are talking about 500 scattering events. And you know that every scattering event, there is an exponential decay in energy. Therefore, this is really challenging inverse problem to solve with extremely low signal to noise ratio. In my lab, we look at all dimensions of light: spatial, angle, phase, time, polarization, and wavelength. And we built computational imaging instruments that, through the control and modulation of all of these dimensions of light, and through correct computational post-processing of the captured data, somehow try to undo the effects of scattering. Scattering leaves its imprint on these various dimensions of light, and if we can somehow read these fingerprints, so to say, then we should be able to undo the effect of scattering and image in high resolution through thick scattering layers. On the top left, I've shown you 2 images, both images taken with a large tissue phantom that mimics the human skull. As light passes through, laser light passes through the skull and comes back, you notice that all you see is a spectral field. But with the right kind of computational approaches, what I'm going to demonstrate in the talk is that you can do reconstruction and produce images of the subjects beneath really thick scattering phantoms, even as thick as the human skull. Okay. In the rest of this talk, I'm going to give you a flavor of the projects in my lab. I'm going to focus on 3 projects. The first one would be ultra miniature lensless wearable and implantable microscopes. The second project I would focus on will be time of flight diffuse optical tomography. And finally, assuming time permits, I will also cover a little bit of camera-based vital signs measurement work in my lab. If time doesn't permit, then I'll just stop with the first 2. Okay? Please interrupt me anytime if you have any questions. I'll try to be slow, but in each of these parts, my goal is not to give you all the technical details. These technical details are in our papers, and so I encourage you to go look at our papers offline. What I'm trying to give you is motivate the problem and tell you a hint of our approach and provide you a sense of where we are in the path towards that solution, so that you get a sense of where the state of the art lies currently. So part 1 is about ultra miniature wearable and implantable microscopes. This is joint work with Jacob Robinson, Richard Baranowicz, Salman Asif, Kaushik Mitra, and Ashwin Shankar Narayanan. Think about cameras, just any cameras, microscopes, telescopes, all the same. Cameras, we've been trying to miniaturize cameras for the last 500 years or so. And we've made tremendous progress in miniaturizing these devices. On the top here is a device that's about 200 years old. It's a view camera. And you can see that from that device, we've gone a fair bit in terms of miniaturization over the last couple of 100 years or so. But right now, you realize that both cameras, microscopes, and telescopes are reaching a limit in terms of their miniaturization possibilities, because diffraction limit and the need for a lens puts certain hard limits on sizes of these imaging instruments. So what can we do? If you look at a traditional camera, the size limits of a traditional camera also true for traditional microscope, also true for a traditional telescope, but let's just focus on microscope for the time being. The size of a traditional camera, especially when used as a microscope, is primarily limited by two things. One, the weight, form factor is all limited by the lens. The lens is big, the lens is heavy, the lens is expensive. Microscope objectives are really the predominant weight and size limiters in a microscope. The second thing that limits the size of these devices is the need to focus light, which means that the sensor has to be placed a focal length away from the lens, even without considering tube lengths and other things that are needed in order to create a compound microscope, which makes the microscope even bulkier. So we started thinking, what can we do? Can we build imaging devices, microscopes, that completely get rid of the lens and still be able to image the human body and get biologically relevant information out? So what we did was our design involved an image sensor on which directly an optimized face mask was fabricated directly on top of the image sensor, about 100 micron or so away from the image sensor. So now the imaging device, the entire microscope, is about the size as shown here. It's about the XY dimensions of the microscope are determined by the XY dimensions of your image sensor itself. And that determines the field of view that you can achieve with this device as a microscope. The thickness of the microscope is dependent on the distance between the sensor and the face mask, and is typically a few hundreds of microns thick. The spatial resolution that can be achieved depends upon the design of the mask itself and the sensor pixel pitch. In practice, we've demonstrated achieving a subcellular resolution, so order of 2 micron or so spatial resolution using these devices. The basic idea is that the captured image, as shown in the middle, does not look like a human legible normal photograph that you are used to looking at, because in a normal camera, a lens does this one-to-one mapping, taking photographs of the scene. Right now, we don't have a lens, we just have this face mask. This face mask does multiplexing, and therefore your captured image does not automatically look like the photograph that you would like to take. But the relationship between the scene and the captured image is fully known, is something that we designed for by designing this face mask. And therefore, that relationship can be unmultiplexed or demultiplexed to produce an output final image. With this, we're able to produce devices whose weight is sub-grams, whose thickness is sub-millimeter. This means that these imaging devices as microscopes can be either on the underside of wearable. So imagine you're wearing a smartwatch. On the back side of the smartwatch, looking at the skin, could be a microscope that's looking at the skin. It could be an implantable. It could be an implantable for all sorts of applications where one might want to image beneath the skin. Many of the applications that we look in our lab are neuroscience and neuroengineering related applications, and I'll show you a few images about that as well. So if we reach this promise, then what we've essentially done is we've taken what essentially looks like a conventional microscope and replaced it with a small, thin, flat device. To look at specimens in a conventional microscope, you would take a glass slide and you would place that glass slide in the slide holder on a conventional microscope. Here, you would just place the glass slide directly on top of the lensless imager, and you can image on chip. This could be really radically transform in-field diagnostics, in-field testing for all sorts of things, from blood tests to looking for bacterial infections to anemia, where the state of the art currently still is to take a piece of a smear of blood on a blood slide and then look at it under a microscope. Now, instead of having to carry a microscope to the field, all you would have to do is to carry this thin device to the field. To give you an idea of the kind of images that we are getting with the device, I'm showing you on the bottom, this is the prototype device with which these images were acquired. This is a device, as I said, about 200 micron thickness. It achieves a spatial resolution of about 2.5 microns. And because of the lensless nature, what it means is that the entire scene is in focus. One can extract not just 2D images, but actually 3D images with the right computational post-processing algorithms. On the top is a captured image of a 3D bead sample. And on the right is the reconstruction of the 3D fluorescent beads. Here is an example where a couple of fluorescent beads were flown through a 3D microfluidic channel, and we're doing real-time 3D imaging using this device. On the left, on the bottom left is an image that shows our spatial resolution. There are two vertical lines that are spaced with about a 1.6 micron gap between them. The image captured by flat scope is shown in the middle, and on the right, you can see the reconstructed image clearly showing that those two lines are clearly distinguished, achieving about a 2 micron resolution or so. And this does not just work on synthetic specimens. You can use this in the field for an in-field microscope. So here are we just took glass slides that consist of fixed specimen of Convallaria monjalis on the left, place the glass slide directly on top of the imager, and you can see an image that's captured. To give you a sense, the cell walls that you see there, they're about 50 microns thick. So that gives you a sense of the spatial resolution in this particular example. On the right-hand side is a video of Hydra vulgaris. Again, glass slide with Hydra vulgaris directly placed on top of the image sensor, trans-illuminated, and you can see we can not only capture images, but also videos at whatever frame rate the image sensor was operating. In this particular example, I believe that was about 30 frames per second. The tentacles of Hydra vulgaris, they are about 30 to 40 micron diameter. So that gives you an idea of the spatial resolution that you're seeing in these images that I'm showing you. One of the driving applications for this project in my lab was the idea of better, is the goal of doing better neuroscience to understand human eventually, but in the beginning, animal behavior when the animal is operating normally in its environment and is subjected to visual stimuli, tactile stimuli, and so on and so forth. The challenge here, especially when we are working with small animals, on the top left is an experiment we did on mice. Especially when we are working with small animals, is that now you want the microscope to be fixed to the animal's head so that you can see the neuronal responses, the firing, the synaptic firings. Currently, there is really no microscopes that are small enough that mice can be freely moving. There are a few labs that are working on different kinds of mini scopes that are lens-based alternatives to what we are proposing here. What we are proposing here currently produces slightly lower resolution, but is significantly smaller and less heavy than that. What you're seeing here is the device directly implanted on the brain of a mice. This mice is freely running on a treadmill in this example. And you can see not only can we get reasonable resolution images of the vasculature, we're also on the bottom able to get functional imaging saying which synapses are being triggered. This is calcium signaling. The details of what it is may not be relevant for this talk. What's important is that every time in this particular mice, every time a particular synapse fires, it releases photons, and we are able to see that release of photons. That's the delta F over F function that we are able to see here. And this release is correlated with treadmill velocity because this is a neuron that is in the motor cortex and therefore is responding to the motion of the animal itself. We've also been able to use this device as an early cancer screening device for oral cancer. Vascular loops in the oral mucosa have been shown to be predictors of cancer. Currently, the way that you look at them requires a biopsy. Because for those of you who have worked with a microscope, you recognize that it is really hard to focus a microscope, even when the sample is fairly static. Now, if the sample is a real live moving human lip, it's not going to be possible or tractable at all to focus the microscope, given its really narrow depth of field. But because our devices have microscopic resolution, but at the same time have very large field of view and depth of field, we can just place this device directly on the lip in order to get these images of vascular loops in the lip, in the oral mucosa. Finally, we've also been able to do some experiments on non-human primates, working with a collaborator in UT Austin, Eyal's lab in UT Austin. So we are really hopeful that this will be the first example of a completely freely behaving monkey whose neuronal responses are being recorded over a wide field of view, real time, as it's freely behaving and responding to both visual and tactile stimuli. On the top left is a graphic illustration of how this device is implanted. Now, in this particular example, the device is implanted beneath the skull, directly on the brain. The device prototype itself is shown on the bottom. You see flat scope, and you see the illumination on the 4 sides. Those are 4 LEDs that are illuminating. And you can see the quality of the images that we are getting from the non-human primate. We can see vasculature that's even 10 micron or 10 to 20 micron sized vasculatures. We're also able to starting to get functional data from the non-human primate as well. One of the things that we're really excited about is so far we have not optimized the mask using machine learning. We have used machine learning on the back end for reconstruction, but we think that there's a lot of hope and potential in using machine learning to both optimize the mask pattern itself. And we think that there's many applications. One of the applications we are excited by is 3D endoscopy, because the size constraints and the requirement for 3D are really something that traditional camera designs cannot really provide simultaneously in this context. And we are hopeful that this technology may be able to provide an answer there. With that, I'll take a short break and see whether you have any questions in this project before I move on to the next project. I'll just take a second to sip a glass of water. So in the next 15 minutes or so, I'm going to do a slide change and talk about a different project. So everything we've talked about lensless imaging, we can set that aside for the time being. There's really not much overlap between these 2 projects. So high resolution deep imaging using confocal time of flight diffuse optical tomography. This is joint work with Jacob Robinson and Andreas Halscher. If you look at current optical imaging techniques for looking deep into the human body, for many applications, imaging the human brain, breast cancer diagnosis, finding lesions in abdominal cavity, looking at a fetus inside the intra-abdominally. For all of these problems, you want to achieve sub-millimeter scales resolution, so hundreds of micron spatial resolution, but you want to achieve that 50 to 100 mean free paths in human tissue. 50 to 100 mean free paths in human tissue is really challenging. And so can techniques be built to use light to get sub-millimeter spatial resolution that deep in the human body? Scattering of light in human tissue basically makes spatial patterns unresolvable. To illustrate that, what's shown on the left is an image, is a high contrast pattern R placed behind 4 millimeters of human tissue phantom. And you can see in the image, there's nothing visible, no contrast visible from that R at all. That's 4 millimeters of human tissue. Now, many of the organelles in the human body that one might want to image are, depending on application, 1 centimeter to 2 centimeters deep within tissue. So if you look at breast cancer diagnosis, breast cancer tumors are typically, even surface tumors may be 4 millimeters, 5 millimeters deep, but deeper tumors are typically 1 centimeter or so deep within the breast. If you look at imaging the brain, the human skull is about 1 centimeter or so thick, somewhere between around that. And so imaging through the skull requires you to image 1 centimeter of scattering. And so, as you can see, even within 4 millimeters of scattering, there's just all spatial information is completely lost. And so we need better techniques in order to see deep within the human body. So what we are envisaging is and working towards in the long term is essentially a helmet or a cap-like platform with embedded sensors and illumination sources on the bottom side of the cap, so that you can use light to both interrogate and measure directly from the human brain. Now, for other applications such as breast cancer diagnosis or for GI applications, the only thing that changes is that the form factor that holds the sensors, the detectors and sources should be different. So there would be different form factors, but the conceptual idea still holds. Right now, we do not have a prototype in which all the sensors are directly implanted in the helmet itself. Instead, we're working with fiber optic light guides in all our current experiments. So how does diffuse optical tomography work? Supposing you have a thick scattering tissue, as illustrated on the top left, and you have a single light source, that's the red point here, and you have a single light detector, that's the blue point here. Both the source and the detector are on the surface. So imagine they are on your head, for example, okay? Or on the surface of the breast of a patient, for example. Now, as the location of the source and the detector changes, you see that the light paths that are traversed between the source and the detector changes. That means what is shown in green here is basically what probability of photons, among the photons that go from the source to the detector, what probability of photons go through that physical location. That's what is being shown here in this particular image. That changes based on, can you give me 1 second? I'm sorry. Hello, is this an emergency? Okay, can I call you back? Sorry about that. So this, as you can see, the different locations of light sources and detectors interrogate different portions of the human tissue. So by changing the location of the light source and the location of the detector, we can interrogate different locations deep within the human tissue. Each of these measurements is giving you a different linear combination of the absorption and scattering coefficients of the entire volume. And so if I can collect all of this information by changing the source and detector location, then I can solve a demultiplexing problem in order to extract the absorption coefficient of the volumetric scattering medium. So that's the basic idea. The basic idea is that I change sources and detectors, I acquire information, I create a linear system. between the unknowns, which is the absorption coefficient of the entire volume, and the collected measurements, which is the intensity measurements for a particular source detector pair. And then I solve a linear set of system of equations in order to extract the volumetric absorption coefficients. While this is great, the current technology has poor spatial resolution, order of several centimeters, and common reconstruction methods are just really, really slow. The key idea that we came up with is the idea that time of flight improves the spatial resolution. So now what I'm going to show you is that I have another scattering phantom on the top, and I have source location and detector location fixed. While the source location and detector location is fixed, as I move the time of flight, again, look at the time of flight, it's in picoseconds. As I move the time of flight, I notice that deeper pixels are being interrogated. Deeper portions of the human body are being interrogated. I can use this observation to throw out early photons and to gather information from deep within the human tissue. So if you wanted to image an object that's a couple of centimeters deep, then you could only collect data that corresponds to, say, 50 picoseconds and greater travel time, and that would allow you to localize only those portions, information only from those portions of the human tissue that are deeper. This reconstruction approach is very similar to DOT. You set up a set of linear equations and you solve them. The only difference is that now every measurement, so for every source detector location, you no longer have a single intensity measurement, but rather you have a time profile. That means your measurements are now 5-dimensional, right? Because the source location can vary in 2 dimensions on the XY plane. Detector location varies in 2 dimensions on the XY plane. And you have, for every source and detector location, you have time information, travel time information in picoseconds. And so you get 5-dimensional piece of information, and you are trying to reconstruct 3-dimensional attenuation map, absorption coefficient over the entire tissue volume. So I'm going to skip the details of the forward model, lest it to say that the forward model can be, if you make a diffusion approximation, the forward model can be written in linear form. In this linear form, mu is the unknown absorption coefficients of the 3D volumetric media. J is what is known as the sensitivity matrix. It's essentially relating the measurements to the absorption coefficients. It tells you it's basically based on the scattering parameters of the media itself. M is the captured measurements for every source detector pair. And so this is the same equation here. Obviously, the number of measurements you are acquiring, it depends upon the number of sources, the number of detectors, and the number of time bins. The number of unknowns depends upon the volume, the number of voxels in the volume. And the Jacobian is therefore this really huge quantity. So typically, even if you want to get reasonable resolution, this would be 1,000,000 cross 10,000 or some really large matrix like that, and making computationally things really intractable. But if we only focus on confocal measurements, that is, if we only focus on measurements that correspond to where the source location is, so whenever I fix a source location, I also fix the corresponding detector location, then I can reduce the number of measurements that I have, reduce the size of the Jacobian. Not only can I reduce the size of the Jacobian, I can also show that the linear matrix that I have is actually a convolutional. And since it's convolutional, I can use Fourier domain techniques to further accelerate the computational complexity of the forward model, making algorithms close to real time, meaning reconstruction algorithms can operate at close to 30 frames per second or thereabouts right now, instead of what used to take about an hour without looking at the confocal or the convolutional approximations. Okay, so here are some results, and all of our results are presented through a tissue scan phantom. So you have a target, and you have a skull phantom on top of the target, so about 9 millimeters of human skull, or a phantom that mimics the scattering properties of human skull. Here are two lines, and these two lines are separated by about 500 micron. And you can clearly see that in the reconstructed image on the bottom right, we can reconstruct the lines, even though in the captured measurements you cannot. Even traditional diffuse optical tomography is not able to resolve these two lines. So you can't get millimeter scale resolution, a centimeter or through a centimeter of skull with traditional diffuse optical tomography, but you can by using the time of flight information. And we can do this real time now by using our convolutional approximation to the confocal measurements. We're basically telling you, this plot shows you why our time of flight diffuse optical tomography actually works so much better. It's because the conditioning of the matrix is much better. So this is a comparison of the singular values of the multiplexing matrix. And you can see with time of flight diffuse optical tomography, is much better conditioned, allowing us to get much higher spatial resolution than conventional diffuse optical tomography. I'm going to show you a few experimental results. These are acquired in our lab using a benchtop laser and a SPAD and a galvo scanning for acquiring the different source locations. Source locations are through a laser that's being galvo scanned. The detector locations are moved by using by using another galvo scanning or by using a 32x32 detector array. Here is through a thick scattering phantom, again, 9 millimeters of human skull. You can see that we can clearly resolve 2 millimeter, even 0.5 millimeter or 500 micron separation between the two lines. Here's examples of targets that we're able to reconstruct. This works whether the subject happens to be absorptive, as is the case here. So you can image blood vessels, you can image hemorrhage, things like that, or whether the target is fluorescent. So you can use fluorescent indicators so that you can look at functional activation of the brain through the skull without having to open the skull at all. The technique, as I told you, gives you real 3D reconstructions. And so here is an example of 3D reconstructions using on a 3D phantom through the skull phantom as well. And finally, we've also been able to use this to acquire in vivo data on a mice. So here the mice skull is much thinner than human skull. So to make our problem harder, we imaged the brain of the mice, but we placed a human skull phantom on top of the mice. And the experiment requires is a touch and visual stimulus experiment. You can see that any time that the touch stimulus is applied, you immediately see activation of the sensory cortex, clearly indicating that the function that the stimuli is leading to activation of the corresponding brain regions. Here is an experiment where the goal is where the mice is looking at a monitor, but is also undergoing touch stimulus. So when the mice undergoes touch stimulus, you see that the sensory motor cortex is lighting up. But when the mice is undergoing a visual stimulus, then the visual cortex gets lighted up. And so the distance between the visual cortex and the sensory motor cortex in mice is 1.5 millimeters or so. And so you can see that even through a human skull, we're getting millimeter spatial resolution for even functional imaging. We really think that this is really exciting for the in-field stroke classification. Stroke patients, neurosurgeons always say time is brain. The time after stroke is critical for functional rehabilitation. Unfortunately, you can't do much at the stroke site before MRI because there are two kinds of stroke, ischemic and hemorrhagic stroke. If it's a ischemic stroke, then you have to treat it with heparin, but it's really, really adverse reactions if it's a hemorrhagic stroke. Currently, in the stroke van, in an emergency vehicle, there's no way of separating the two. And so patients are brought back to the hospital before MRI to detect whether it's ischemic or hemorrhagic. This kind of a wearable device potentially could distinguish between ischemic and hemorrhagic stroke. allowing you to administer heparin in the field. And so this would be a tremendous advance. Okay. I realize I'm running out of time, and so I'm not going to spend a lot of time talking about camera-based vital signs measurement. Let's do to say to add just one. This thing is that we've also been able to use these camera-based devices for measuring pulse oxygenation. I know that in the talks, I was in the talks before, and there was not much talk of oxygen saturation measurements, and we are able to show oxygen saturation measurements as well. Here is a patient undergoing, a subject undergoing voluntary apnea, and you can see their oxygen saturation dropping and coming back up during a voluntary apnea experiment. With that, I will stop and take any questions. Again, thank you all for attending, and thank you organizers for inviting me to give this talk.
Thank you, Ashok. Great presentation. Really, really interesting work. Audience, if you have questions, please put them in the chat channel, and I'll ask them just for convenience. So first question, how sensitive is the lensless camera to shifts in location? Like when you're doing these animal experiments, is it pretty rigidly attached? If you had it on, say, a smartwatch or some kind of wearable device that someone's wearing around, would it matter if the motion was displaced, or if the position was displaced?
So the field of view. So I'm going to answer this slightly differently. So the field of view of the device is about slightly larger than the sensor physical sensor size. So if you're talking about physical sensor sizes of the order of 7-8 millimeters to a centimeter or so, then that's your field of view, and shifts within that field of view don't matter. But of course, if you want to image a particular artery, but your watch itself is not on that artery, then of course you don't get imaging. It's not sensitive to small shifts. It's just sensitive to really large motions. In one of the projects that we have ongoing, a collaborator from Texas A&M is building what is known as they call it a barcode, but it's basically something that's a chemical reagent that senses blood glucose level and releases light based on blood glucose level. So it's a fluorescent indicator. So when you shine light, then it binds with the glucose, and the amount of fluorescent light that's emitted from this barcode is proportional to your glucose level. And this would be a barcode that's implanted beneath the skin, so interstitially. So it's like it's implanted, and the idea is that this smartwatch would then be sitting on top of this barcode and collecting data from this barcode. In this case, the data that we are after is a point data. It's just from one barcode. But there may be relative shifts between the barcode and the imaging device itself, and up to a centimeter or so of relative shift, we can still image with the same device.
And related to that question from Wenjin, I think is linked. Is it likely to be possible to be able to do this not without contact? Like, so it would the lenses cameras kind of make sense in a non-contact scenario. So
these are, I mean, these work both in contact and non-contact scenarios. There are some examples where you want contact. There are some where you don't want contact, and we've shown examples in both cases. In the experiments that I showed you, most of them are actually either direct contact with the human tissue, or at least there is an interface between the two. But we've also shown it for as simple applications as photography, where there is absolutely no contact at all. Another application that we recently showed in SOCAD is actually the same camera put on a virtual reality platform to look at the eye in order to do eye gaze tracking and eye gaze estimation. Again, in that context, it's non-contact.
Got it. Yeah, makes sense. Question from Jeremy regarding SpO2 estimation. Does it face similar calibration challenges that we find in blood pressure estimation?
So SpO2 has calibration challenges, but they are not similar to blood pressure at all. They are much better understood. They are the calibration challenge that we have is that the primary calibration challenge is a clinical challenge. Ideally, you would like an SpO2 monitor to cover the entire range all the way from 65-70% SpO2 to 99% SpO2. And there's no easy ways of actually getting humans non-clinically to be at that low oxygen saturation stage. And so there is a validation challenge. It's not similar to BP at all, in the sense that once calibrated, the SpO2 devices work very well, and they are not necessary to be personalized. I think in blood pressure, calibration tends to be very personal. For SpO2, calibration does not tend to need to be personalized.
And just to follow on from that, is it based on your answer, then it's robust to melanin content and lighting, because that's
correct. So it's fairly robust to melanin content and lighting, because the two wavelengths that are used in SpO2 measurement are wavelengths that are specifically chosen to minimize these artifacts.
Mm-hmm. And a similar related question from Dang Dang. Is the image sensor attached to the forehead in your SpO2?
So in that example, the image sensor is attached to a helmet platform with so the gap between the forehead and the platform is not forced to be zero. You're not forcing contact, but it's really close.
Great. And then
just a very quick question that because also for the infant monitoring, we find that the skulls of the infant is very thin, so we can measure SpO2 from the brain, the brain area of the baby. Do you think it's that possible that we simulate the camera as a non-contact apneas, like to use the camera to measure the brain activity of the neonates?
So I think the diffuse optical tomography stuff that I talked about is very close to FNIRS. I think of diffuse optical tomography as basically FNIRS on steroids, right? Lots more sources, lots more detectors than FNIRS. So typically both diffuse optical tomography and FNIRS is SNR challenged. And so if you are non-contact, then you're wasting a lot of photons, right? Because and so that's a challenge. We have not looked at it. We've not looked at time of flight diffuse optical tomography for non-contact, but maybe it's worthwhile. I mean, even if you're non-contact, if you're really close, it might be okay. Right now, the way we are working on an experiment where we are trying to build this thing up for measuring the SpO2 of pregnant sheep. The goal is to build a transabdominal fetal SpO2 monitor using the time of flight diffuse optical tomography. So currently, if you want to measure the SpO2 of a fetus, there's really no method to measure that of the fetus without doing it intrauterine, meaning you put a probe inside the uterus, which of course is dangerous for the fetus and sometimes even for the mother. We have very promising preliminary results there. So maybe those results can have bearing to what you asked. So now that I make the connection, the answer is probably yes. I think it's maybe we can talk offline, but I think there's ways to do that. It's a great idea.
Cool. And then on the topic of the diffuse optical tomography, as a non-expert in this specific domain, it seems very similar to EEG measurement. there obviously seems some advantages to what you can do with this, some potentially disadvantages in the same way that measuring PPG compared to ECG might have different levels of sensitivity. And do you imagine that for the diffuse optical tomography could become more practical for the types of applications that EEG is used for, in like brain computer interaction?
I mean, our the large portion of our effort is in brain-computer interfaces using diffuse optical tomography. Is a project that's funded by DARPA to build brain-computer interfaces using optics. So that's just context. Now, to actually address the technical question of what's the difference between EEG and where we stand right now, I think EEG has been as a method for measuring function from the brain. So it's responding. There's no structure measurement possible with the EEG, right? So you're getting function. You're getting electrical impulses. They get centimeters resolution, so it's really coarse resolution. Spatially, temporal resolution is pretty good. So tasks like classification, they are very amenable to and really useful. Currently, with the diffuse optical tomography state of the art, the time resolution is still limited, less than that of EEG. Spatial resolution is getting better, almost an order of magnitude better, right? Like from centimeter, we're almost able to go to millimeter resolution. So that's significant. So the capacity, if you think of it as a brain-computer interface, we imagine that the capacity of these optical interfaces to be several orders of magnitude more, because you have 3 dimensions, and in each dimension, if you have one order of magnitude improvement, that'll be significant in terms of the capacity of the interface itself. But it's not yet robust, which means the current experimental evidence in terms of brain-computer interface using this technology is less impressive than current what you can do with EEGs.
Got it. Great. Thank you very much for your presentation, for the question and answer, and really interesting topics that I think many of us are still new to many of us in the community here. So really helpful to learn about those, and exciting to see the progress.
Thanks a lot. And thank you all for inviting me, and thank you for listening. And you can read more about our work in either of these 3 websites. Thank you.
Thanks, Ashok. So now we have a paper session where we have 3 papers, all on the topic of blood pressure estimation or measurement from imaging systems. And then after that, we're gonna have a Q&A, short Q&A for those 3 papers. So during these talks, if you want to put questions in the chat, please do, and let us know which paper they're directed to. The first paper we're going to start with is contactless blood pressure measurement via remote PPG with synthetic data generation using generative adversarial networks. So if the author of that paper could share their screen, and I can unmute you. Is that Li Wen? We can currently see the presenter view. That's great. Thank you.
Okay, good. Okay, can everyone hear me?
Yep, we can hear you.
Okay, and so let's start the presentation. Hello everyone, my name is Li Wen from National Yanmin Jiao Tong University, Taiwan. Today, I'm going to present contactless blood pressure measurement via remote PPG with synthetic data generation using generative adversarial network. There are two kinds of approaches for blood pressure measurement through PPG signals. One is by calculating the time of phase difference between two signals, such as post-transit time or post-wave velocity. And the other is based on waveform feature analysis from a single signal, such as the area, the slope, and the spectrum energy. Recently, the RPPG signals are taken into account for contactless measuring. However, the morphological property of the RPPG signals may be far from the ones of the PPG signals. Some subtle features barely exist in the RPPG signals. The deep learning approach is applied for high-level feature extraction instead of the handcrafted waveform features. However, the lack of the data is an obstacle to the training procedure and evaluation. In this study, a multi-channel end-to-end model is proposed. The RPPG signal from the upper and the lower half phase are leveraged as the model input, which contains the information of some phase difference and more waveform features. The idea of the infogun is adapted here for generating training data with controlled age and BMI combination. And the augmented data is expected to fluctuate correspondingly to subject information and to solve the insufficient data issue in model training. Here shows the overall structure of the proposed method. First, with the sequence input visual image, we obtain two RPPG signals of the upper and the lower phase as the model input. Second, we statistic age, BMI, and systolic blood pressure for all of the subjects in the training dataset to create a table for model selection. To solve the mentioned issue of data scarcity, the synthetic data generation with infogun is employed here. During the augmentation procedure, age and BMI were considered as two control factors, so the synthetic blood pressure fluctuated correspondingly. In the implementation, some modules are pre-trained with the training structure shown in the subfigure B and C. This pre-trained step aims to obtain a generator with prior ability to generate fake RPPG data and a series of F and B with prior ability of blood pressure estimation. The model fine-tuned with the pre-trained weights tends to converge to a better result. Next, I'm going to talk about the RPPG dataset used in this work. To conduct the assessment on the RPPG case, we cooperate an IRB with Chang'an Medical Foundation, located in Taiwan, to collect the data for camera-based blood pressure estimation. About 1K participants in the collected RPPG dataset, aged from 18 to 92. The results of the RPPG dataset are presented here. The proposed baseline model structure can achieve the lowest MAE among all existing approaches. Furthermore, with the model selection, the MAE can be further reduced to 10.15 and 8.84 for SBP and DBP. And the MAE is reduced to 9.13 with model selection and the synthetic data generation procedures. And the proposed method elevates the performance of the hypertension groups efficiently. And thank you for your time and attention.
Thank you for the presentation. Our next paper presentation is titled Remote Estimation of Continuous Blood Pressure by a CNN trained on spatial patterns of facial pulse waves. Thanks, Rago. We can see your screen, and I think you're unmuted, so please go ahead when you're ready.
Okay, can you hear?
Yep.
Thank you. Hello, I am Ryogo Miyazaki from Chiba University in Japan. I would like to make a presentation about remote estimation of continuous blood pressure via convolutional neural network trained on spatial patterns of facial pulse waves. This is about research background. It is important to bring continuity, convenience, and remoteability into blood pressure measurement. This is derived from the gap between desired components for blood pressure measurement and the current situation of blood pressure measurement. The gap is the lack of convenience remote method to measure continuous blood pressure. Then, camera-based methods could satisfy the requirements. There are some camera-based methods to estimate continuous blood pressure. This is a representative method which is based on regression in a feature space of facial pulse wave. In this method, there are mainly three limitations. First, this method is based on one spot pulse wave. Second, this method is based on a simple machine learning. Third, this method is based on a window processing. Then we will bring three contributions: spatial information pulse, deep learning, and unnecessity of time width. This is about research overview. Our goal is continuous blood pressure estimation based on deep learning with spatial information of pulse wave. This is process flow of this research. First, extraction of facial pulse. Second, spatial description of facial pulse. Third, estimation of blood pressure based on CNN. Fourth, construction of data set. Fifth, assessment of the proposed method. This is about extraction of spatial pulse wave. This phase is composed of three processes. First, setting ROIs into RGB video comprehensively. Second, extracting pulse wave from each ROI. Third, spatial reconstruction based on coordinates of the original video. This is about phase to convert spatial pulse wave into spatial pulse contour descriptor and spatial pulse beat descriptor. This phase is composed of two processes. First, extracting pulse contour information and pulse beat information from each coordinate of spatial pulse wave. Second, spatial reconstruction based on the coordinates of the original video. This is about estimation of blood pressure based on deep learning. This is architecture of deep learning. This architecture is based on ResNet and CVPM. The inputs are spatial pulse contour descriptor and spatial pulse beat descriptor. The outputs are systolic blood pressure, mean blood pressure, and diastolic blood pressure. This is about dataset construction. Here, blood pressure variation is induced by breath holding. The dataset is constructed from 10 subjects. This is experimental environment. We use blood pressure monitor and RGB camera. This is the result of blood pressure estimation based on the proposed method and benchmark, which is multi-layer perceptron. The blue line is estimated result, and the red line is ground truth. The horizontal axis is time. The vertical axis is mean blood pressure. This chart is concocted by the test dataset by 6 subjects. This result shows that the proposed method has higher estimation accuracy than benchmark. This is about summary and future work. This is the limitation of the conventional method. And this is contribution in our study. This is our future work. First, learning metadata such as weight or height. Second, interpreting the deep learning model. Third, generalizing the proposed method to other tasks such as emotion recognition. Thank you for your kind attention.
Thank you for the presentation. And our third and final presentation for this part of the workshop is regression or classification, reflection on blood pressure prediction from PPG data using DNNs in the scope of practical applications. And just 1 second, let me unmute you. Okay, Mirko, you should be good to go.
Can you hear me?
Yep.
Okay, cool. Yeah, my name is Mirko Fuchs from the Leipzig University of Applied Sciences, and I'm the presenting author of this paper. The paper is on regression or classification, reflection on blood pressure prediction from PPG data using deep neural networks in the scope of practical applications. So there are several deep learning-based approaches for blood pressure classification and regression, but to the best of our knowledge, there is no research that directly compared these approaches to each other, and therefore the main focus of our work is to compare them. And in particular, we were interested in the question whether classification-based prediction is sometimes better than regression. So why should this be the case? Roughly speaking, because classification doesn't care about the ordering of the target variable, and while regression does, of course, and this is somehow a looser constraint which might be beneficial for some target applications. For instance, if a very highly accurate blood pressure value is not required. And of course, the loss functions are also different for both approaches, which might lead to different behaviors during training and therefore also to different results. We just wanted to know whether the prediction performance depends on the size of the target bins in the particular blood pressure range segmentations. And also, previous research found that personalization is very important for blood pressure prediction, and we therefore were also interested in how effective personalization is, and if there is a difference for classification and regression-based approaches. And we also finally raised the question whether personalization might be more effective in case of narrower bins. For our research, we used the arterial blood pressure and the PPG signals from the MIMIC3 database. More precisely, we selected windows of a length of 7 seconds from both signals, and we used the PPG sequence as input for our networks and the ABP sequence to estimate the systolic blood pressure as the mean value from the systolic peaks in this time window. We used 4 different segmentations in our study, which are shown on the top right here. The HPH and DGK represent segmentations according to the German Cardiac Society, and the even 4 and even 10 are artificial segmentations with 4 and 10 blood pressure bins of equal size. Now in our analysis, each bin in a particular segmentation corresponds to a target class, and the ground truth target class is derived from the continuous ABP value by assigning these values to their corresponding bin. And the target class is actually what we also want to predict. So for classification, this is straightforward. We directly predict the target class. And for regression, we first predict the continuous blood pressure value and finally assign the predicted value to its corresponding bin in the segmentation under test. And then we compared the performance of these approaches by measuring the accuracy of the predicted classes. We divided our data into training, validation, and test sets, and we first trained AlexNet and several variations of the ResNet architectures, and the results of these networks correspond to pre-personalization results. And we also applied personalization. That means we selected 10 subjects from the test set and use 10% of their individual data to fine-tune the networks. The figure shows the combination of results that we obtained from all deep learning architectures on the test. So let's first concentrate on the dark shaded blue and red boxes. They correspond to the performance before personalization was applied. We can see for none of the blood pressure segmentations is there a clear tendency that the classification outperforms regression and vice versa. If you compare the results with respect to different segmentations, we can conclude that the performance drops with respect to the size of the bins. So that means if the bins get narrow, or in other words, if the segmentation consists of more bins, the prediction performance drops. Let's now incorporate the light shaded boxes in our analysis. They represent the results after personalization. And from this figure, it's clear that personalization drastically improves the performance, which can be observed for all segmentations here on the left. And here's another view on pre and post personalization results. One can see that the relative amount of the performance improvement is larger for narrow bins. So while the performance after personalization is more than twice as high here on the left side, it is improves by more than a factor of 3 here on the right side for narrow bins. That means that personalization seems to be more beneficial for narrow bins. Finally, we also found that personalization is consistently more effective for classification than for regression-based methods. That means classification performance is always higher than regression-based performance after personalization, which we can see here on the top row. This brings us to the end and to our main conclusion that classification-based methods might be preferred if a coarse segmentation is sufficient for the particular application. Thank you.
Thank you for the presentation. So I'm now going to invite all 3 speakers to unmute, and we can start the Q&A session. If the audience has additional questions, please post them in the chat and let us know which paper they're directed to. So the first question is for Li Wen. And the question is, what are the feature importances of age and BMI in the GAN training? Is it, do you have to necessarily include age and BMI so that the mean absolute error accuracy of blood pressure prediction is enhanced? Let me just invite you to unmute again. Just 1 second. Okay, we can hear you now. Yeah.
And the age and BMI is not necessary during the GAN training, but these 2 factors are regarded as such as the key for calibration step. And
That's great. And if you can just stay unmuted, that'll be easiest for the Q&A, just because each time you mute, I have to unmute you. So that'll just make it easier. Okay, and one other question for you, Li Wen. Is there just one blood pressure measurement performed per video? And is this data set available for other researchers?
So far, we only perform BP measurement once on each data set, each video. And the continuous BP measurement is still the study progress, so it's not in this paperwork.
Great. Question for Ryogo. How much does the breath holding task impact your results? Does it also increase participants' heart rate? And could you be measuring heart rate changes rather than blood pressure? I think this is one of the big challenges of blood pressure measurement, is finding ways to change people's blood pressure, but without necessarily high correlations between other features that might be measured, if that makes sense.
Okay, thank you for your question. We perform breath holding to obtain different variations of blood pressure. Breath holding can lower blood pressure. Am I answering your question?
Yes, did it also raise or lower the participants' heart rates in a similar or correlated manner?
Yes.
Does that question make sense? Was there a high correlation between heart rate and blood pressure in your data set? If you don't know, that's okay.
Sorry, I don't know about this.
Okay.
Sorry.
No problem. No problem. For Mirko, is there a difference between classification and regression? Sorry. Is the difference between classification and regression whether the last layer is a classification head or regression head? Are the number of parameters for the same for the two prediction heads?
Okay, yeah. Thank you for this question. Yes, essentially the only difference between these different methods is that the prediction heads are essentially either classification or regression heads. And therefore, I think the number of parameters are not equal because for regression we have only this continuous target variable, and for regression, for classification, of course, we have parameters according to the number of output classes. But this is, I think, the only difference. And yeah, from that perspective, all other parameters in the networks are actually the same, or the number of parameters is actually the same.
And Wenjin, do you want to ask your question? I wasn't sure if that was towards one specific paper or not.
Yeah, that's general, but also maybe to the last one, because in your results, the personalization is a very important step for the high accuracy of the blood pressure monitoring. So do you think there's a way to measure this personalized data from the video to assist the calibration, to improve the calibration? Otherwise, if you want to use the model for a new subject, if you don't pre-train that subject, it's hard to use. But such a pre-training step is not the typical step in real applications.
Mm-hmm. Yeah, it's also it's really an interesting problem because even the personalization that we applied is not, I think, a personalization that can be applied in practice, because we selected the personalization data for fine-tuning in a way that ensured more or less balanced distribution of blood pressure ground truth values from all the bins under test, and this is what you can't really do in a realistic scenario.
Yeah.
If you focus on data maybe on the first few minutes or few hours even of a subject, even then you cannot ensure that that the blood pressure is modulated in a way that you have enough information. So I think this is really a particular problem with blood pressure prediction, and that's also the reason why we also here focused on PPG. We also have some research on RPPG, but I think it's not yet solved in PPG only, and therefore it's important to concentrate on these issues.
Yeah, but for PPG, if you collect, for example, the gender, age, BMI, body height, do you think that you can make this model more robust if you get this data from the subject?
I'm currently skeptical about it, to be honest, because we have done a lot of work in this area, and this is really, I think it's really difficult to be highly accurate only due to these additional information like sex and age and so on. I think it's really problematic, and I'm really looking forward to do more research in this topic. But yeah, I don't know if we can get there. Yeah.
And one additional question. Of course, as you noted, blood pressure is continuous. Even classification could be treated as an ordinal task, which is somewhere kind of in between regression and classification, traditional classification. So did you find a bimodal predictions, and did you think about incorporating a loss that captured ordinality in the classes?
That's interesting, but we have not looked into this particular detail right now, so cannot unfortunately cannot comment on this.
Okay. Thank you once again to the authors. Very much appreciated those presentations, and we're keeping well on time. So we have 5 more presentations in this final session, and we're moving a little bit away from the PPG and video-based vital signs into camera-based activity monitoring and health applications of those. So we've got 5 presentations. Once again, please put questions in the chat. Let us know which paper they're directed to, and we'll have a Q&A after this final paper session. So the first paper is multimodal transformers for nurse activity recognition. And so if the speaker would like to share their screen, I'll unmute you.
Okay.
We can hear you. Yep.
Perfect. Thank you so much. Hi, my name is Momal Ijaz, and I'm going to be presenting my work, Nurse 8, a multimodal transformer for nurse activity recognition, which I did with my fellow Renato Diaz and under the supervision of Dr. Chen Chen from University of Central Florida in Orlando. So nursing is a very important profession, not only in US, but globally. It's a very important part of the healthcare workforce. Currently, there are 3.8 million registered nurses in US alone, but US is expected to see a shortage of nurses by 2030. One of the main reasons for that is the high professional turnover rates for the nursing profession. That is around 17.2% for the last year. And that is because the nurses, of course, are exhausted. Why exactly is that? Among all the duties that a nurse has to perform throughout the day, and the high workloads and long duty hours, nurses have to manually enter all the duties and all the work that they perform into an inefficient electronic health record system. This job alone takes 25 to 50% of a nurse's day. And if they make any mistake during these manual entries, that can lead to tragic and fatal errors. US alone sees 250,000 annual deaths just because of incorrect EHR entries. So this is a very serious problem that we are trying to solve. How exactly are we trying to solve? We are proposing a novel nurse activity recognition system using infrared cameras and acceleration signal from the smartphone in the nurse's chest pocket. And we are trying to automate how activity recognition and how the manual entries are performed usually into an electronic health record system. So for performing nurse activity recognition system, we are proposing a transformer model, a novel transformer model, which will basically perform activity recognition. And it does pretty well as it achieves state-of-the-art performance of 81.8% on the nurse activity recognition challenge data set that we have used for our study. There are 3 main contributions of our work. First is dual modality. We are proposing that instead of just relying on the skeletal joints data from an infrared camera, one should also fuse it with acceleration signal, because that leads to a 5.2% better activity recognition performance. We are proposing a novel fusion technique for fusing acceleration and skeletal joints data. Instead of just simply adding them, if you use this technique, you'll get to see a 6.8% better activity recognition performance. Last but not the least are both these two novel contributions actually lead us to get the state-of-the-art performance on the data set that we are using for our study, and it outperforms famous deep learning models like spatiotemporal graph convolutional network, LSTMs, GRUs, and traditional machine learning algorithms like KNNs by a whooping 1.6%. So a little bit deeper dive into the method that we're proposing. Our model comprises of two main parts. First is a spatiotemporal skeleton model. This model takes skeletal joints data, which is coming from an infrared camera that is focused on a nurse. This model extracts spatial and temporal features using transformer encoders. And in the output tries to predict that what activity is the nurse exactly performing. The second model is an acceleration model, which takes acceleration signal from the smartphone placed in the right chest pocket of the nurse. It's also a transformer-based model and tries to predict the class of the activity that the nurse is performing. Our final model, that is a multimodal transformer model, which is our main model proposed in the paper as well, utilizes both spatiotemporal skeletal and acceleration signal, fuses them using a novel cross-view intention, and tries to predict the class of the activity that the nurse is performing a lot better than the single modalities. So how good is our method? Well, we've compared it with the previous works that were carried out on the data set like KNN, STGCN, Random Forest, GRU, and CNN. And our transformer-based method, which is using acceleration and skeletal joints data, achieves the highest validation accuracy on the data set of 81.8%. Besides that, we have carried out individual activity-wise comparison as for of our method with all the previous related works of the data set using the accuracy and F1 score metric, and our method is constantly outperforming all the previous works on that as well. Graphically, we can see here that these two methods are the top two previous best performing methods. These light colored bars are reflecting that F1 score of the previous methods is pretty low for all the activities as compared to our proposed method. And this high colored diagonal streak is reflecting that our method is pretty intelligent and accurate in predicting the classes of the activities that the nurses are performing correctly, and the error rate is pretty low. So in conclusion, we have three main contributions. We have proposed an attention-based fusion technique for better activity recognition. We are presenting a new perspective to solve the problem of activity recognition. That is, instead of just going for skeletal joints or just acceleration, one can try fusing them both, because that actually gave pretty promising result and help us achieve state-of-the-art results on the challenge data set. There are some areas of improvement. The data set that we use was skewed and smaller in size, so one can actually evaluate how good actually your method is on larger data sets. One can try pre-trained models as well, because transformers tend to be data hungry. So if you want to extend our work, here's the GitHub code repo link for our work. Thank you so much for listening.
Thank you very much for the presentation. Very interesting work. Our next talk is titled, "Should I Take a Walk? Estimating Energy Expenditure from Video Data."
Okay, can you hear me?
Yep.
Okay. So I'm Quinn Peng from Karlsruhe Institute of Technology, and I'm supervised by Professor Heiner Skipperhagen. And today I will give the talk regarding should I take a walk, estimating energy expenditure from video data. First is the motivation. Since the camera-based human health monitoring system has attracted a lot of the attention from the computer vision field in recent years, and most of the people want to monitor their health status during their daily life, which makes the monitoring of human body energy expenditure a valuable choice, since it is directly linked to the human mental health and human body health. However, most of the existing works focus on monitoring human body health through wearable equipment, which limits the comfort and is especially not very convenient during the COVID period. So thereby, we are motivated to create an end-to-end camera-based human energy expenditure estimation system, which uses the contactless camera data as the input. So in order to tackle this issue, we proposed the video to burn this site for calorie consumption estimation task, and two versions of this site, which are video to burn diverse and video to burn ADL. This site targeting at different types of actions in human daily life are proposed. Video to burn diverse this site targets at mostly sports activities, which contains a large range of fluctuation for human energy expenditure. And the calorie annotation is obtained through a combination of online category-wise calorie consumption resource and the skeletal-based energy expenditure calculations. And on the bottom part of this slide, you could find some statistics of the proposed this site. Video to burn ADL, this site is targeted at household-related activities and fine-grained activities which contains a relatively small calorie consumption range. And the annotation for human energy expenditure is obtained through the combination of physical measurement and skeleton-based calculation. So for this fine-grained activities, there is no online resources regarding the calorie consumptions. Then I will give a short introduction regarding the acquisition of the calorie consumption annotation for each day site. For video to burn diverse day site, the activity category-wise annotation is obtained directly from the online resources mentioned by our paper. And for simple-wise annotation, we use the skeleton-based calculation to generate the fluctuation individually for each sample inside one activity type. And the fluctuation against the category-wise annotation is obtained through the ratio between the current sample skeletal moment intensity and the maximum moment intensity selected in all the samples inside one action type. Then we use this ratio to multiply with a predefined fluctuation range, such as 100 calorie, to generate a deviation for each sample against its category-wise annotations. And for the video to burn ADL, this site annotation or activity category-wise is obtained through the physical measurement of heart rate data. And we use these formulas to calculate the energy expenditure individually for male and female. And the participants will be it's 4 people from our lab. And we average the final results to get annotations. Here are some samples from our video to burn diversity side with its simple-wise calorie annotation. On the right-hand side, we compare our data site with the other human energy expenditure data site. We can find that we have more video clips compared with the others. And also we have simple-wise annotation in addition to the category-wise annotations. And then we conduct our experiments based on existing video feature extraction backbones, including R3D, R2P, 1D, slow fast, and I3D, together with 2 kinds of the evaluation settings. The first setting is called as known activity types, which means that the training and testing shares the activity types for human energy expenditure estimation. And the other is for new activity types. That means that the samples in the testing set are all unknown activity types compared with the training set. This is for the generalization estimation. And our major metric for the calorie consumption estimation is chosen as the mean average error. And consider the both setting, slow fast backbone shows great performance for the human energy expenditure estimation task. And it can achieve 34.5 errors for the calorie estimation for known activities. And also it achieves the second best for the generalization test. And also on the right bottom, we could find a visualization of the convolutional layers of ICT model. And we can find that most of the human body regions are focused. Here is the experimental results for the video to burn ADL data set and the corresponding inference time and the number of parameters of the leverage models. Then it's the conclusion. So in this work, we contribute 2 data sets regarding different activity intensity of human daily life, and also 2 kinds of the annotation settings. And we provide 2 evaluation settings, and one of them are targeted at generalization estimation. And we also conduct the experiment to test the performance of currently existing video classification backbones for this task. And also during the experiment, we found that the generalization of currently existing video classification approaches is not that satisfied. So there is still large space for research in the future in this direction. So for the next step, we would arrange the calorie consumption into metabolic equivalents to provide another annotation for our data set and develop a novel backbone to tackle the generalization issue. So thank you for your attention.
Thank you very much for your presentation. Third talk is human stool classification for gastrointestinal health based on improved ResNet 18 model with dual attention mechanisms. Thanks, Jing. Let me just unmute you.
Can you hear me?
Yep.
Okay. I'm honored to be here to introduce our work, Human Stools Classification for the Gastrointestinal Health, based on an improved ResNet 19 models with the dual attention mechanism. I will, for the part 4, to introduce our work. The part 1 introduced our background and the primary works. The background is the SNOO are related to the health of the human gastrointestinal function. Primary classification of the shape and colors of stools can diagnose the health status of the people. It is for the early detection, early treatment. The detection of the stool has 2 methods. The one is object microscope detection and chemical analysis, and the other is the subject. Its shape, consistency, and colors. It will be the bruised stones, the formed skills. It's clinically varied classification skills. Difficult and primary contributes has the 3 points. The first, the results of the color recognition will be disturbed by the urine in the toilet. The second, loose stones are distributed throughout the toilet with no solid piece. Some pictures contains the stones of various of shapes. So build a new human stool immediately is important. The method of our stool network will complete both the color and the shape classification test simultaneously. Accuracy of the shape classification is 94.4%. Accuracy of the colors classification is 99.8%. Let's introduce the method. Our method is the stool network introduction. The introduction can be divided to 2 parts. One is fully convolutional network architecture, include the convolution layer, and it regards as the future extractor. The other is the classifier part, which is composed of the 2 classifications, hence for the color and the shape. This is the dual attention. We can edit it, and the performance is work well. Let's introduce the dataset description. It provided a piece of black cardboard and placed the black cardboard about 1 meter above the toilet. The light on the individual's mobile phone was turned on and the light source was passed through the blackboard. The small holes illuminate the stool area in the toilet, and then the phone camera is used to take the picture. The experiment and the matrix dataset was random divided 5 times, and each divided dataset was treated 5 times in the network. The average of value of the 25 test result and the 95% confidence and interval and are used critically for the evaluating the performance of the models. Let me see the result. In addition, we treat the stall night and rest night 18 times, count the result on the test site each time, and then define the hypothesized H0 as there being no significant difference between stall night and rest night 18, where H1 shows there is a significant difference between the two. The statistical significance level was selected. The p-value is equal to the 0.0001, and it is indicated that there is a significant difference between snow night and rest night 18. We have compared our work to the others network and the attention mechanism. You can see we have got the worked well. Let's introduce the conclusions. The snow night reached the current state of the art performance in the multi-task classification of the snow. Did not use a significant segmentation network to extract the ROI in the image, because CNN has learned how to discuss the background area in the image in the hair layer. Data inheritance for the only few class stand off for the old class, which makes the model perform better. Thank you for your attention.
Thank you for the presentation. Our next talk is predicting mind wandering with facial videos in online lectures. If the author could share the screen. Thanks.
Okay. I hope you can hear me well.
Yep, we can hear you.
See my screen. Yeah, thank you. Hi, I'm Taekyung Lee at KAIST, and I'd like to introduce our paper predicting mind wandering with facial videos in online lectures. So with COVID, many offline lectures has turned into online formats, and there is a significant problem in online lectures that people tend to be out of focus, which we call mind wandering in online education compared to offline manner. To be more precise, students have more chance of mind wandering in online learning, which is a significant problem because it leads to poor learning performance. There has been several approaches to enhance learning experience utilizing attentional state prediction, gaze tutor or attention-aware learning technology, for example, provides interventions by making pop-ups, calling their student's name, or asking questions to students during online education. However, they all utilize existing eye-tracking-based attention prediction system. For example, you can see here that there is an eye tracker attached to laptop to predict their attentional states. However, the main problem here is that eye tracker is not applicable and distributable in real-world scenarios. So we wrap up existing attentional state prediction technologies limitation by these three factors. First is the existing attentional state prediction technology requires specialized hardwares, for example, eye trackers, as we told, and other EEG, EDA, or fMRI devices. Also, even though they utilize specialized hardware, they suffer from low attentional state prediction accuracy, for example, 0.51 F1 score. Also, a few researchers try to utilize facial videos for webcam videos to predict someone's attentional states. However, they are evaluated only in controlled environments, lab environments of film viewing scenarios, so they are not directly applicable to real-world lecture scenarios. Therefore, we present PAVE, facial video-based attentional state prediction framework, by only utilizing the webcam to predict students' attentional states. Our contribution follows a PAVE framework and also the first public in the wild video data set, the vision data set for attentional state prediction. The main problem before conducting our experiment was that there lacks of public vision data set for attentional state prediction during online lectures. Therefore, we conducted in the wild experiment to collect the data set during online learning scenarios like this. So we recruited 37 participants from 7 universities in Korea by periodically asking participants to periodically report their attentional states during 1 hour video lecture taking scenario like this. So participants periodically press the keyboard button to respond whether they were focusing or not in the time they were hearing the probing beep sound. And by collecting the data set, we could wrap up with the in the wild data collection problem that there were some unreliable probing responses, that some participants were actually drowsing, but they were focusing on the lecture. So to remove such unreliable responses, we manually labeled participants for browsing or not and made this unreliability metric to remove such participants. And by so, we present the first public in the wild facial video data set with 15 participants and 15 early brief facial video with total 1,100 probing points of attentional state focused or mind wandering. And by this data set, we now want to predict whether someone is focusing or not. And by utilizing traditional attentional features, utilized in various sensory domains, we adapt their features into vision-based domains of facial emotion, eye aspect ratio, head movement, and gaze. Eye aspect ratio represents someone's eye size with respect to their facial landmark position. Of course, they're participant dependent, so we make normalization. And by extracting the features and their statistics, we found that there are 13 significant features of attentional states, including eye aspect ratio. And we trained the classifier with XGBoost, a support vector machine, and deep learning models based on those features. And we show that our feature-based method outperforms random prediction baseline and gaze-only feature baseline, as shown in the graphs. And this is our contributions again. Thank you for watching my presentation. And if you have any questions or want to chat, you can contact via email or chatting. Thank you.
Thank you very much for your presentation. And now we have our final paper of this session. Don't forget to add any questions to the chat. We'll be having our Q&A after this presentation. So the final presentation is strain detection based on breath and motion features obtained by a force sensor for smart toilet systems.
Can you hear me?
Yep, we can hear you. Thanks, Rina.
Hello, everyone. I'm Rina Go from Panasonic Industry, Japan. Today, I'd like to present my paper, and the title is Strain Detection Based on Breath and Motion Features Obtained by Force Sensor from Smart Toilet Systems. First of all, why it is important to detect strain. As the global population ages, health monitoring technology is seeing a significant growing interest in recent years. The elderly people are more likely to suffer subarachnoid hemorrhage, cerebral infarction, and cardiac arrests. Many of these occur in the bathroom, and the probability of death increases when detection is delayed. And from previous research, defecation induces cardiovascular and blood pressure changes, and it has been found to associated with cardiac arrest occurrences. Therefore, it is crucial to prevent onset of the disease by notifying the user for long and or strong strain. So we propose a smart toilet system that uses a pressure sensor to detect strain in protecting privacy. Here, I'd like to talk about our proposed system. Figure below shows the flow of our system. A pressure sensor is placed on the toilet seat, and this sensor is consisted of 144 small cells. Time-series data such as the second image is acquired. The average depth pressure sensor and sensor of gravity and respiratory pattern are calculated based on the sensor values. The respiratory pattern signal is estimated by applying ICA. A total of 22 features are engineered from each signal, and action classified as strain detected by random forest. In this research, we classified 5 actions performed when subjects were on the seat: no motion, strain, strong strain, weak strain, writing paper, and wiping. The lower left shows the flow of our experiment. 5 actions are performed continuously with a break in between. The experimental environment is shown in the lower right. A conventional laser sensor was set behind the subject as a comparison method. And here, I'd like to show you our result. Left figure shows average accuracy when the test data is random sampled and tested 50 trials. From left to right, using laser sensor, average value of pressure sensor, center of gravity, respiratory pattern, and our proposed method. Accuracy's proposed method has improved from 61.6% to 80.2%. And right figure shows a confusion matrix of 5 actions by our proposed method. Weak strain and strong strain were difficult to detect compared to other actions. Without distinguished from weak and strong, the accuracy of the strain recognition was also 92%. Finally, summary and future works. We propose a system for strain detection using only pressure sensor. Proposed system classified 5 actions with an accuracy of 80.2%. And future works increase the number and variety of subject. Since the number of subject is small and there are many male subjects, and subjects were asked to perform as they normally do in this experiment. However, this may differ from the actual action. We would try to obtain data under actual conditions. Thank you for kind attention.
Thank you very much. I'm now going to unmute all of the speakers from this session. And if you can just remain unmuted for the Q&A so that we don't have to unmute everyone multiple times. Just give me 1 second. Okay, let's see. So Momal, can you, I'm requesting you unmute. Yeah, great, thanks. And Jing, can you also unmute?
Yes.
That's great. And can you? Great. Yeah. Okay, I think that's everyone. Great. So there were some questions in the chat. I know folks answered some of those questions, but we'll also repeat them for the benefit of the audience and give you opportunity to elaborate a bit. So the first question I had for Momal, I asked if you were doing any reconstruction of the accelerometer from the video. The reason for asking that was, it seems like an interesting way to maybe pre-train the network because you have some sort of noisy or weak labels from another modality. I was just wondering if you consider that for future work or any possibilities of kind of training off of one modality to learn representations for another.
That could be a very interesting application, but that I think in itself is another dimension of research to explore, because the camera data that we are using, it's not RGB video camera, it's infrared camera. So for security purposes, only data that we are getting is skeletal joints. So that I think needs some more research work, that how exactly we can extract acceleration signal from skeletal joints. For our study, the acceleration signal and skeletal joints data was provided separately. So we just fused the two to do better activity recognition.
Okay, great, thank you. And then a question for the stool classification paper from Wenjing. What are the applications that you envisage? Like how would this kind of be deployed in practice? Yeah, I think you wanted to know a little more information about how you collected your data set, if it was like crowdsourced, or how do you recruit your participants?
Okay, thank you for your questions. We collected the stool image by the volunteer. After they use the toilet, we provide a piece of the black cardboard and place the black cardboard about 1 meter above the toilet. The light on the individual's mobile phone was turned on, and the light source was passed through the black cardboard. The spool holes illuminated the stool area in the toilet, and the phone camera is used to take the pictures. So we collected the data set.
So is this all in one location? Is that correct?
Yes.
Yeah, okay.
Yes, thank you.
Okay, and a question from Dang Dang for the paper, should I take a walk? First part of the question is, CNN activation seems to be highly related to the body locations with high motion. How do you recognize the load or intensity from the CNN activation map?
First, thank you very much for the question. I agree with you that CNN-based approaches may be highly related with the body locations, which has a high motion level. In the future, work we tend to crop the human body with a certain near body regions, and also we want the network to figure out which kind of the workout with which kind of the load they are using. Since different kind of the equipments with different kind of the weights, they have different kind of the appearance. So that is exactly what we expect the network to learn from the camera data. Yeah, so I think that will be mentioned in our future work. And thanks for your question.
And related to that is, our activity recognition and energy estimation two separate problems, do you think, or is it better to treat them just as one? Like, would it be better to model them as two separate tasks?
Okay. So from our experiments, we found out that they are more likely to be two separate tasks, since the mentioned CNN-based approaches, actually they work pretty good on the video classification and action recognition based data set. But from our result, it can be shown that they also have high generalization issue and also doesn't perform very good on the carry estimation. So I think the carry estimation is a more difficult task compared with the action recognition. Yeah, thank you for the question.
Mm-hmm. Okay. And then question for the mind wandering paper for Taekyung. What were the distinguishable features for mind wandering? Do you think they generalize across people and across contexts of lectures? For example, some topics might require more visual attention, such as a lecture, say on design, or with a lot of visual imagery. Other lectures might not require as much visual attention if a lecturer is describing something without a lot of visual, like visual cues on the screen, for example.
Thank you for your question. I think that's a very interesting point. For the first one about like features generalizable between subjects, we checked with statistical tests that our features generally apply, like eye aspect ratio features apply for most of the participants equally. And for the lecture content, although we didn't weight the intensive experiment in our data set and in our lecture scenarios, like although that course of AI for Everyone by Professor Andrew Ng is kind of fixed format containing PowerPoint slides, we actually wanted to find that kind of aspects differences between like lecture containing a lot of text or lecture containing a lot of figures, or like Andrew Ng himself showing up, but we could not find like significant differences between them.
Okay, thank you.
Thank you.
And question for Rena. How much do you think that you could do if you just had a very simple, like single IMU or accelerometer on the smart toilet versus like a full kind of pressure sensitive, like full pressure sensor around the rim?
Excuse me, I didn't catch your question. Your question is how much sensor?
Yeah, how much do you think spatial information is important versus could you do sort of similar? How much would accuracy, I guess, be affected by just a single IMU attached on the device compared to a full pressure sensor? Does that make sense?
I'm sorry. IMU sensor?
Like accelerometer, just like a thing, because for scalability, right, you might need to find a cheaper solution than for the sensor, right? So a low resolution sensor.
We didn't try that, but it's a good idea. It's our future works, maybe.
Okay.
Thank you.
Okay, I think that brings us to the end of our questions here for this session. So once again, like to thank all of the authors, presenters, and to our keynote speakers. Really enjoyed the workshop, very interesting breadth of work. And we look forward to hosting more of these workshops in future and continuing to provide opportunity for the community to gather. Please do reach out to other members of the community if you're interested in collaboration or to continue conversations. Part of the purpose of these workshops is to make people aware of all the work that's going on and foster those connections. So really really glad that we had so many people attend over the course of the workshop today. This session has been recorded, so we believe that will be made available by CVPR, but we'll find out more details after the workshop. We do have a best paper selection, which was made based on the reviews of the papers, as well as the presentation today during the session. And we're delighted to announce that the best paper award for the workshop goes to the paper on efficient remote PPG with temporal derivative modules and time shift invariant loss. So I think that was Joaquin, that was your paper. Very great paper, and I think can be very useful for people training not just PPG, but other types of physiological sensing models from noisy signals, as well as poorly synchronized or just signals with labels that come from a different location on the body. So congratulations.
Yeah, congratulations. Very nice work. Yeah, and also later that the best paper prize, your name will be mentioned on our website, so you can refer to that in your future work or in your CV. Get the best paper prize in a CVPR workshop. Congratulations. Yeah, and also in the end, we also want to mention that following, it's definitely not the end of our field. We will continue our efforts. So we organized a special issue for the GBHI this year, following this workshop. So you all are welcome to extend your paper and submit to this GBHI journal, which is a very nice journal with a good impact factor. So, but you require to have this more than 70% extension on the content, and the deadline will be the August of this year. And the review starts as soon as you submit. So we encourage you to extend your paper and to this journal paper.
And if you plan to submit, then do feel free to let us know, so that we can plan accordingly and recruit reviewers and things like that. So it's very helpful to know ahead of time how many submissions to expect.
Yeah, thank you all. Thank you.
Great, thank you, everyone. And yeah, feel free to continue discussions. I'm not sure if there's a way I can unmute everyone, but if I can, then we could give you all the opportunity to continue talking. Let me try that. So I think everyone's been offered the opportunity to unmute. So if you want to continue any discussions, then please do. But the workshop's officially ended. So that's all. Thank you very much, everyone.
Yeah, and also looking forward to your future participations. Okay.